Welcome everyone to the third edition of POM. We're going to get started in about 4 minutes. While you're waiting, we'd really appreciate it if you filled out our pre-event survey. The link is on your screen right now. Thank you very much, and we look forward to welcoming you in a few minutes.
Good morning, good afternoon, and good evening to day 2 of the third Photonics Online Meetup. My name is Orad Reshef. I'm from the University of Ottawa in Canada, and along with Professor Andrea Armani from USC, I'm the co-chair of today's event. We are very excited to have you here today. We received over 1,000 registrations from all corners of the world, and today we are featuring 3 speakers from 3 different continents. So we are proud to say that we were able to present to you a truly international event. Let me begin by acknowledging the generous support of 4 organizations, this Photonics Media, the Center for Research in Photonics at the University of Ottawa, the Joint Center for Extreme Photonics at the University of Ottawa and the National Research Council, and the USC Viterbi School of Engineering. They have combined to foot the bill for this entire conference out of pocket, so that everything you see here, from the poster session to the booths in the career fair, is absolutely free to all participants. You can learn more about these organizations at photonics.com, at photonics.uottawa.ca, at extremephotonics.com, and at viterbischool.usc.edu. As a note, we are live streaming all of the sessions to YouTube today, but it is unfortunately with a significant delay of about a minute. So for this reason, our chairs will be much more likely to address any questions you might have if they're asked directly in Zoom. Questions are encouraged to be asked as early as possible in the talk, as opposed to at the end of the talk, so that all the other members of the audience will be able to vote on them, and comment on them. So let's try and make this event as interactive as possible given the circumstances. Speaking of interactivity, our little organization has come a long way in the last historical year. So new to this edition of POM is an entirely virtual conference center that also hosts a virtual poster session and a career fair yesterday. So in the breaks between these sessions, we invite all of you to join us at this conference center, which is in Gathertown, to network and mingle. Also, please fill in our event surveys. This is the best way to get your feedback to us to help us back to the organizers to help us improve all of the events for you. So if you need any of these links, so links to the Zoom stream, to the conference center, to the survey, as well as the conference program, all of these links can be found in your inbox in an email with the subject line POM21 important links. Now, we have an excited day planned for all of you with presentations on 3 topics selected by you, our audience, in a survey that we sent out a few months ago. Our 3 topics for the event today are on metasurfaces, on biosensors, and on frequency combs. And so now, without further ado, to kick off our Metasurface section, I will now introduce our first topic share, Dr. Sean Rodriguez, a senior scientist from the Toyota Research Institute of North America. So he will be chairing the first session. Please take it away, Sean.
Thanks, Orad, and thanks for that introduction. Welcome everyone to the Photonics Online Meetup Metasurface session. Again, my name is Sean Rodriguez. I'm a senior scientist at Toyota Research Institute of North America in Ann Arbor, Michigan. I'm very excited to be chairing this year's POM. We have a number of great speakers this year. Before we get started, I want to thank all of our attendees for joining today, as well as the rest of the Metasurface committee, Mara Caglion from Tampere University and Arka Majumdar from the University of Washington for helping with the selection and planning process. Finally, I'd like to thank all of the POM team for working tirelessly behind the scenes to get this POM conference up and running, especially Dr. Orad Reshef and Professor Andrew Armani, who co-founded this conference. Before we get started, just a quick reminder to type your questions into the Q&A throughout the talk and upvote the questions you think are most important. Please don't wait till the end of the talk to ask your questions. So let's get into it. Our plenary speaker for this session is Professor Jason Valentine. Professor Valentine received a bachelor's in science and mechanical engineering from Purdue University in 2004 and a PhD in mechanical engineering from UC Berkeley in 2010. Later that year, he joined the faculty in the mechanical engineering department at Vanderbilt University, where he is currently an associate professor and the deputy director of the Vanderbilt Institute of Nanoscale Science and Engineering, VINS. Professor Valentine's past and current work includes the development of optical metamaterials, optical cloaks, dielectric metamaterials, and hot electron devices. His work has been selected by Time magazine as a top 10 scientific discovery. And at Vanderbilt, he has received an NSF Career Award, the Office of Naval Research Young Investigator Award, as well as the Chancellor's Award for Research. Please go ahead, Professor Valentine.
Thanks, Sean. Let's see here. Share my screen. Okay. Yeah, so thanks so much for having me. Thanks to Orad and Andrea for organizing this. I remember actually 3 years ago talking to Orad about the first conference. Little did you know that every other conference in the world would be following your lead in 3 years. But it's a pleasure to be here. I'm going to talk about some recent work in our group concerning meta-optics or metasurfaces for image processing. So, in terms of image processing and convolutional neural nets, these systems, deep learning and CNNs, have really revolutionized the way we process data and make decisions on data for a wide range of applications. We're going to talk about image processing today. So this would include things like object classification, localization, segmentation, so telling where in the image the object is, recognition, so being able to locate objects in an image, and classify them, image enhancement, medical image analysis. It's really revolutionized the way that we go about these things. But convolutional neural networks and deep networks and these new forms of digital image processing come at a cost. And it's really a computational cost. Okay, and we'll talk a little bit more about frame rates and limitations in frame rates in a second. But if you take a look at a deep neural network, it has obviously many layers. And the layers have different functions, for instance, convolution and pooling. And if you take a look at the most costly layers in terms of computation, those are the convolution layers. Okay, and so for this VGG16, this is a kind of a benchmark classification system. 99% of the computational time is involved in the convolutions. And in fact, most of that computation time is up front where you're dealing with a full image. So what happens is you go through this network and the data set gets reduced until you make a decision based on that data. But at the front of the network, you're dealing with a full size image. You're dealing with usually 3 colors. And so the majority of the computational costs are up front, okay? And these first layers are really convolutionally heavy. And so if you take a look at what's actually being done there, at the front of the network, you're identifying low-level features, okay? And as you move through the network, you get to higher and higher level features in, for instance, in classifying this image down here as an Audi A7, okay? And what's important for the context of this talk is that these low-level features are really edges, okay? These are really mostly edge filters. And this is oftentimes the most time-consuming portion of a classification network. In fact, there's a whole field of study just on edge detecting algorithms and how to do edge detecting more accurately and also faster. And so, for instance, just to give you some numbers, if you take standard data set, this is a standard edge detecting and kind of benchmarking data set. Take 2 very common ways of doing edge detection: the Canny algorithm, which is an analytical technique that would limit for this size of image, your frame rate to about 15 frames per second, and a CNN-based, a convolutional neural network-based edge detector, like holistically nested edge detection, would limit your frame rates to about 2.5 frames per second. So those are pretty big barriers in terms of doing high-speed image processing, classification, recognition. So what I'm going to talk about today is a technique where we want to offload some of this computation into the optic. Okay, so to replace the front end of optical systems with a meta-optic, and that meta-optic would perform some portion, and today we'll be talking primarily about edge detection, some portion of the computation. The benefits of this approach is that the optic itself can be extremely high speed. The optics that we're talking about today, the passive optics operate at the speed of light. Okay, they require no input power. Okay, so you're reducing power consumption and you're reducing the amount that you're needing to do digitally. You're reducing the computational requirements for the system. In addition to doing things in optics, you access additional information channels. Okay, so a typical focal plane array, you're going to get an intensity image and that's it. With metasurfaces, optics in general, you can access things like polarization, phase, momentum. Angle of incidence is a big one. We'll talk about that today in terms of edge detection. And so this can allow you to do more in the optics than you can on the digital side. So today I'm going to talk about 3 different areas, and I'm going to really make an effort to leave time at the end for question and answers. Okay, so I may pick up the speed a little bit at the end so that we have some time for you all to ask questions. But I want to talk first about passive edge detection and differentiation, compound meta optics, so doing multiple functions in one optic. I want to talk about recent work on dynamic edge detectors, so being able to image in bright field or in the edge mode at your choosing. And then talk about scalable fabrication of meta optics, essentially scaling meta optics to relevant apertures in an effort to reach realistic devices. Okay, so we're talking about image processing using optics, and this, in fact, is not a new area of study. Optical processing based on Fourier optics is a very old field. And takes advantage of the fact that you take an object and you put that image through a lens, and that lens performs a Fourier transform. And so you can operate in the Fourier plane. You can do convolutions in the Fourier plane. Then you come back in the image plane, and let's say, for instance, you see the edges based on what you've done in that Fourier plane. Okay, I flipped the image here to make it upright, but it would be flipped upside down in reality. So we're going to talk about edge detection today, and in particular, differentiation. So if we took this system and we wanted to perform the second order derivative on the image, in the Fourier plane, we would take the convolution of, we take the Fourier transform of the image, okay, that's g of k of x, okay, and we would convolve it with a function in of k. And for the second order derivative, we would multiply it by k squared, okay, the second order derivative. We then have another lens, do another Fourier transform, and get back into the image, but now it has been differentiated. Okay, to accomplish this convolution in this 4F system, we would have a filter where the transmission of the filter was proportional to k squared. And because this is the Fourier plane, we're in the Fourier plane, this means that the transmission is proportional to the position squared. So you have a filter which blocked light at 0k, and then as you went to larger k, the transmission increased as the position squared, or k squared. Okay, so this is conventional technique for doing second order differentiation. This is a 4F system. You can actually make these correlators in many different configurations, but you'll notice they all have multiple lenses and they all are multiple focal lengths long. And so when we looked at this problem, essentially what we wanted to do is take the system and instead of operating in the Fourier plane, let's make a filter, okay, a metasurface filter, where the transmission of the filter itself was a function of the in-plane wave vector. And we want to make a filter in this case which performs the second order derivative, okay? And so the transmission, or the transfer function, to be specific, must vary or must be proportional to the in-plane wave vector squared. And if we can do that, and then we can put a lens on the backside, we can form an image of the second order derivative of our original image. So that's the goal, okay, here. And we aren't the first folks to think about this. There have been some other techniques for doing this, proposed and demonstrated in the literature. For instance, using surface plasmons, doing 1D differentiation, photonic crystals for 1D differentiation as well. What we really set out to do was, one, we really want to do all directions. We want to do 2D edge detection, but we also wanted to broaden the bandwidth, the operational bandwidth. Bandwidth is information, essentially. So you want to be able to get as many photons in the image as you possibly can. You'll want to be able to work at a relatively high numerical aperture. That's essentially your field of view of your differentiator. And we want to be able to make everything a flat optic, and we ask ourselves, you know, can we also make this thing dynamic? Can we switch between bright and edge imaging? All right, so to be specific, the ideal transfer function for performing the second order derivative, so performing the Laplacian on the incident field, okay, would look like this. So S and P are the S and P polarization components. You have your S in and S out and P in and P out, the diagonal components here. You have off diagonal, which are polarization conversion components, okay? So converting from S to P, and those should all be a function of the in-plane wave vector squared, okay? They all should be proportional to the in-plane wave vector squared. So the actual filter that we're going to make is going to be based on a pretty simple structure, silicon rods in a polymer, okay? And it's a periodic structure. It's perfectly periodic. It's a photonic crystal structure. And we're going to take advantage of the fact that for p-polarized input, okay, you can design it such that the transmission as a function of incident angle here, which is shown in the top right plot, can follow this kx squared within a certain frequency bandwidth. And I can explain more about how this works in the Q&A if you want. But essentially, we have a guided mode in where we are using interference between the incident field and the guided mode to control the transmission as a function of incident angle. So it's p polarization, and we'll talk about this more in a second. S polarization, on the other hand, at that particular frequency range is completely reflective. So S is not going to actually perform the second order derivative, but it's going to be filtered out from the image automatically. We don't need to use polarized input light because the filter itself kicks out S polarized light. All right, so in our case, the actual transfer function we're getting is S is going to 0, and we're only dealing with p polarized light, and we have no polarization conversion, so the diagonal component is 0. Okay, and if you take a plot along that line versus kx, this is transfer function versus kx, you'll see that you follow this kx squared relationship for kx up to 0.3 or numerical aperture up to about 0.3. Okay, so again, that's connected to your field of view and also the throughput of your filter. Okay, so we have this dependence, and the phase also stays very, very flat. So we have the response we want, at least theoretically. Experimentally, this is what the filter looks like. So again, it's just silicon rods. And this is a Fourier plane images where the filter is off, because this is actually just a wavelength where the filter is not providing the second order derivative. And you can see the Fourier plane is uniform, meaning we are allowing all angles in. And then we go to the working wavelength of the filter, and you see that the Fourier plane is now filtered. And if we take cross sections along the Fourier plane, you see that we have this kx squared dependence along the different directions in the Fourier plane. So we have successfully realized this kx squared transfer function up to a numerical aperture of about 0.3. Okay, so what does this look like in a real imaging system? Well, essentially what we've done here first is take a test chart, so Air Force test target, and we place the filter directly behind it. And we just image this in a conventional inverted optical microscope. This is the bright space or bright field image of the test target, so the wavelength and resolution. And these are the edge images. So these are with the filter in place now. And you can see that you see all of the edges of the image. And if you took a line scan through there, you would see kind of the double hump profile of a second order derivative every time you hit the edge. So it's an experiment and then the calculated second order derivative. So good agreement between the experiment and the theory. What's also nice is that even though we don't have the perfect second order derivative across a broad wavelength range, we have something which is close to it over about a wavelength range of about 200 nanometers. So you have a fairly high numerical aperture and you have a fairly large working bandwidth for your filter, which essentially means throughput. You can get light through the filter for imaging real objects. So we wanted to do that, and so we take the system, and these are cells now. So these are onion cells, bright field image, and the differentiated image. So again, this is just filter on, filter off. You have no other parts of the microscope that we're changing. And this is, again, across a broader bandwidth. So you can see you get really nice, clean images using this approach. Again, conventional microscope, just placing a filter in that microscope. And this could happen right behind the sample. It could also happen right in front of the camera. Okay. All right. So that was not a compound optic. That was a filter and a conventional lens. But what we would really like to do is get to a meta optic, which is comprised of multiple metasurfaces, where you can actually not only differentiate the image, but form the image. So we can replace all of the components in the optical system with metasurfaces. And to do this, we use a technique which we've been developing in our lab for a while now, where we make multiple surfaces on separate substrates, and then we bond them together in an elastomer, okay? Similar to the way you would do like a lithography operation where you align a mask and place a mask on a surface. We're aligning surfaces and then solidifying the surfaces into multi-layer, multi-metasurface compound optics. And we've been exploring a lot of different functions, for instance, phase control at different wavelengths, polarization control, phase and amplitude control. So using very different types of metasurfaces placed together to get different types of functions, similar to the way you would line optics on a table, filters and lenses, for instance. So for this particular function, we're doing differentiation. We need to make the differentiator and we need to make the lens. And so these are images. These are patterned using E-beam lithography. And you can see peeling off the differentiator, we place it on top of the lens. What's also nice about this system is there's no need to align on the optical axis. Okay, so in a 4F system, you have to have your filter perfectly aligned along the optical axis. Here, the filter is uniform. So there is no there's no need for precision and alignment between the lens and the filter. You put them together and you can use this as the complete optical system. We have no extra lenses in this system. The meta lens is doing all the imaging and the differentiator is providing the edge information. And so this is bright field and the differentiated images, again, of those cells. So a little bit more noise in the images than in the inverted microscope, but that's really a function of the meta lens not being that optimized. So these are passive systems, right? You have filter on or filter off. You can change wavelengths to change the functionality from bright field to differentiated images. But we more recently have been thinking about how do we dynamically switch this? Because in a real image processing system, oftentimes you would want a bright field image. You don't want the unadulterated image and then the edge image, but in particular for image segmentation operations. Okay, so we would like to be able to dynamically switch between these operations. So for instance, this is a design where the filter actually does nothing. So this is the working wavelength for TM polarization. The Fourier plane is uniform, so the filter is providing a bright field image. And then for this particular design, if you strain it, okay, so you take this is ideally in an elastomer, you take the elastomer and you stretch it, you can switch it to the, you can switch the period of the metasurface, which will switch you in to this second order derivative frequency band. Okay, so you change the transfer function by changing the period of the metasurface. And this particular design has this kx squared dependence over numerical aperture of about 0.25. Okay, so this is the design we actually want to try to make. We're already, in making the metasurfaces, we're already putting them in elastomer. So they're already in elastomer, which we can strain. And so we just have to get the design right. So we built a little strain system on our microscope. So we're going to take the metasurface, peel it off an elastomer, stretch it, and look and see how the transmitted image changes as we strain. So remember, this really only works for TM polarization. So this is TE and TM, and at zero strain. Okay, actually this is not this is labeled strain, but this is essentially stretching. Okay, so 100% means unstretched. Okay, so it's the original, no strain on it. And so you can see both of the polarizations transmit uniformly across the incident angle. Okay, so they don't have really this kx squared dependence. As we start to stretch the material, so from 100% to 136% stretching, you can see that the TM polarization changes. Okay, so we go from something which is fairly uniform to something where we get this kx squared dependence at the 136% level, while TE polarization actually gets filtered out. So that transmission goes down and down and down as we transition into the differentiated image. And so you can look at the Fourier plane now, and we're using the input light is polarized. And so the vertical direction on the Fourier plane represents the TM polarized light coming through, and the horizontal direction here represents TE light. So originally, both are transmitted equally. And then as we start to strain the structure, okay, we notice that both go down at first, so the image gets darker, and then we transition into this kx squared along the vertical direction, so TM, the TM polarization getting the kx squared dependence. And if we take a look at the actual imaging here, so we have bright field image, so unstrained, okay, 100%, and then we go to 136%, and you see that bright field transition to the edge image of these are the cells again. And if you take a look at another type of objects, this is kind of looks like a tube. Starts bright field, and then we go to the edge image as we strain the system. So we can dynamically change between a bright field and a differentiated image by changing the period of the structure dynamically. And you can start to imagine something like this being used in a segmentation network, where you take your object and you differentiate it, you feed that to a neural network, and you also feed the unadulterated image, the bright field image. And you're trying to figure out where in the image the objects are, or segment the image into its different objects. Okay, the last thing I want to quickly touch on is scaling these things. So being able to make them at large scale over relevant apertures. Okay, and this is something our lab has been working on for a little while now. We previously had developed a large area patterning technique using nanosphere lithography, where we assembled the spheres onto a surface of silicon. We shrink the spheres, and we use those spheres for an etch mask to make periodic patterns. And this is pretty straightforward. We built this for, and we can certainly implement this for the edge filters. The edge filters are perfectly periodic. This allows you to get to aperture sizes which are relevant for common apertures in imaging systems, and they work really well. But the question is, how do you make something which is non-periodic? And so that's a technique which we have recently developed, where we're still using nanospherical lithography, but instead of using nanospherical lithography directly as the etch mask, we use the nanospheres as lenses to expose a photoresist below them. And we don't give uniform illumination, but we use grayscale illumination, where we can change the intensity level as a function of position, and thus change the size of the patterned rod as a function of position. And you can compare this to UV stepper lithography. We're not going to have as much resolution necessarily as UV stepper, or at least if you go to extreme UV. But there's a big benefit in terms of rapid prototyping, because your mask size gets very, very small. So one of the problems with patterning trillions of unit cells is that you have very, very large masks, and it's actually difficult to implement those masks. They're so large. Whereas here, everything is translated into grayscale, allowing us to have very, very small mask sizes. And so these are some recent results of making lenses. Lenses are a nice kind of base structure to start with, because you can characterize them really easily. So these are the grayscale pattern, and then the actually fabricated lens and some imaging using those lenses. And the lenses actually come out really nice. So they have fairly high diffraction efficiencies, diffraction limit focusing, even though they have a few defects from the self-assembly process. So I think you can take these types of optics and scale them to relevant sizes. And that also really is the number of information channels. So the larger you can make the aperture, the more information channels you're going to have to work with in terms of image processing. So with that, I'll conclude and just say that I think there is a lot of prospects for replacing the front end of these image processing systems of optics, and you can get high speed while also reducing the power consumption and reducing the computational requirements. And again, I think you can scale these things to relevant sizes for doing these things. And so with that, I'll leave this up. Thank my collaborators and open the floor to any questions.
Great. Thanks, Jason. Thanks for such an excellent talk. There's a few questions coming in the Q&A, and I'm going to start reading off some of them. The first one is, what is the max strain you can apply without breaking the structure completely?
Yeah. So that would really be dependent on the material you're using. We're using PDMS here, and we are at about the max strain that we can get before tearing the PDMS. And it's actually more of a function of stress concentrations where you're actually contacting the PDMS rather than the strain limit of the PDMS in the middle of the array. So, but right now we're kind of at the max we can get with our strain device.
Great. Another one coming in from Corey Aiden. Says, amazing work, Jason. Can you tell more about the broadband operation? What is the bandwidth? I guess you showed operation between 1130 and 1180 nanometers in the first part of your talk. And then I can read the second question after that. So the operational bandwidth is a little bit hard to pin down because you don't have of course the perfect second order derivative as you get out into away from the center wavelength. So we've done imaging at around 200 nanometer bandwidth, and it looks fine. It's not the perfect second order derivative out at the edges. I think the more interesting question is, what's the bandwidth when you start to pair this with like a digital network to do segmentation? And because the digital network can correct some of the kind of error in the edges out at the edges. And so I think the question is, how accurate can segmentation be based on the bandwidth you're using? But it's about 200 nanometers kind of nominal, by eye, you could say. Gotcha. Great. We have another one here from Victoria Babicheva, and it says, if there is time, it'd be good to hear more about the modes under oblique incidence that Professor Valentine mentioned earlier in his Q&A.
Sure. Yeah. So I can show that. I have this slide kind of getting the little more of the nitty-gritty details of what's happening in the structures. So you can model this with coupled mode theory. That's what this is. But we've actually modified coupled mode theory so that the quality factor, the damping of the modes, is a function of the incident wave vector. Okay. So essentially, what you have is you have a bound state in the continuum or a quasi BAC, depending on how you illuminate it. Here at 1200 nanometers, that's kind of away from our where we're operating, but we still the wavelength we're operating at, we still have some of that. We still have a fairly high Q. Okay, which is trapping light in the plane of the photonic crystal, but it's leaky. Okay, it's not a bound state, it's quasi bound, and it's that interference between the leakage and the incident wave that gives you this angle dependent transmission. So you can model it with this coupled mode theory. We back out quality factors based on just periodic simulations like MPV based band structure calculations where you find Q as a function of in-plane wave vector. You plug that into the coupled mode theory, and you find almost a perfect match between the full wave simulations and the analytical theory.
Thank you. Great. I have a question for you too. You've shown some great work with coherent light so far, but I was wondering if there's any chance that, or maybe what the next steps would be towards achieving incoherent light differentiation.
Yeah, so one thing that I think is interesting is taking advantage of the fact that with these structures, one of the benefits of Metasurface is you can put a lot of different things on the same wafer, on the same aperture, very different structures. And And I think one of the interesting directions is using that freedom to do multi-wavelength edge detection. So using, say, each filter for a 200 nanometer bandwidth, but having different center wavelengths in different regions, and taking advantage of the wavelength multiplexing as information channels. That's image processing. You're almost always, usually it's visible image processing. You're almost always taking advantage of RGB or some combination of those colors as information channels in classifying. So I think using distributed aperture type systems for increasing information channels is a really interesting direction.
Yeah, exactly. I think if there was a way to match the filter to the metasurface location, you could definitely have some good opportunities there.
And that also actually kind of plays to the benefit. So one of the problems with the lenses, right, is the lenses are also fairly narrow band in terms of their dispersion, and you can actually you don't have to fight that if you do a distributed system like that.
Nice, thank you. So I'm looking at the questions again, and I see one. For your differentiating photonic crystal, you need this quadratic transmission profile. Did you design for that, or did you stumble upon it accidentally? How would you design for a different polynomial, for example?
Yeah, so that's a good question, and really we kind of stumbled on it. We were trying to make something dependent on angle. We were targeting K vector dependent transmission profiles, and we kind of stumbled on this one more or less. But that's an interesting question. How do you do what we're also very interested in is making more complex profiles, and I think you really have to go to some type of inverse design to do that. It's very challenging from a first principles standpoint to get that. In my experience, there are a different class. We've explored a bunch of different classes. We can do different types of. We can do low pass filters, high pass filters, band pass filters. We have designs for all those. But they're not necessarily like from first principles. It's more like stumbling upon these designs. So doing something more complex is probably going to get in the inverse design realm.
Right. Yeah, we had a great talk from Jelena Jukovic yesterday on inverse design.
Yep.
So let's see there. One more question here. From YouTube, Andre Andreev, what are the temporal parameters compared to Paco cell, for example? Does that? Yeah,
for the dynamic edge detectors, they're slow. I mean, you're dealing with strain. At least in this case, it's slow. You can imagine combining this with like a MEMS type architecture for modulation instead of using this kind of bulky, kind of this thing that we use stage-based modulation. But it's never going to be super fast, at least for this particular approach. For something where you want to do fast, like frame rate type speeds, you're probably going to have to use a different technique like a liquid crystal or something like that to do the modulation. Because I mean, it's a photonic crystal, so we can change either the period or the surrounding media to modulate the response, and so liquid crystals would be a good option for that.
Excellent. Well, I think that about rounds it up with the time, and so I want to thank you again, Professor Valentine, for joining us today and sharing this great work.
My pleasure. Thanks for all the questions. That was fun.
Okay, so we had a number of great submissions this year for POM, and I'd like to just point out that the next 3 speakers that we have talking were in the top 5% of abstracts submitted. And I'd also like to remind the audience to please send your questions during the talk so that we can get plenty of discussion going on between everybody. So our first presenter is Charlie Rayman from the University of Exeter. Go ahead, Charlie. Thanks.
Okay, thanks, Sean, for the introduction. And good evening to all of you from the UK. I'd first like to thank all of the organizers for giving me this opportunity to present this work to all of you. And also congratulations on organizing another fantastic online conference. I'm sure it takes a lot of hard work behind the scenes. So I'm going to talk to you about how you can generate and tune artificial magnetic fields in metasurfaces. Now, this theoretical work was done in collaboration with Simon Horsley and Eros Mariani, both at Exeter University. So why are we interested in artificial magnetic fields? Well, if you look into the textbooks, you'll see that the interaction between charged particles and real magnetic fields gives rise to some of the most interesting and important phenomena in physics. For example, classically, we have this Hamiltonian for a charged particle in a magnetic field, which couples through the vector potential A. And this gives rise to the well-known Lorentz force, QV cross B, which can deflect charged particles into cyclotron orbits. And then in quantum mechanics, we have the Schrödinger equation, which gives rise to the Aronoff-Bohm effect. And then for large magnetic fields, we have Landau quantization of the cyclotron orbits, where the continuous spectrum splits into discrete energy levels called Landau levels. And this also gives rise to the famous quantum Hall effect. But what about photons? Well, photons are neutral particles. They don't have an electric charge, and therefore they do not directly couple to the electromagnetic gauge potentials. So all of these interesting magnetic field related phenomena remain elusive for photons. So this begs the question, can we somehow simulate these effects by generating an artificial magnetic field? And there have been several interesting ways proposed in order to do this. But in this work, we're going to focus on probably the most straightforward way, which is through strain engineering. Now, this concept originally emerged within graphene physics, where it was shown that the electrons propagating through a graphene membrane that had some strain pattern associated with it, then the electrons behave as if they were subjected to a large magnetic field, so-called pseudomagnetic field, which could mimic some of the properties of real ones. And the key advantage of this approach is that it has a purely geometrical origin, which means it can be translated into entirely distinct physical systems. So let's take a few steps back and try and understand why these pseudo-magnetic fields emerge in graphene. So graphene is a monolayer of carbon atoms arranged in a honeycomb lattice, as shown here. And the essential electronic properties can be captured by a very simple type binding model. So here we just consider the kinetic hopping of electrons between nearest neighbors with a hopping amplitude T. And the hopping amplitude is the same for the three nearest neighbors. So if we diagonalize this Hamiltonian, we obtain the famous band structure for graphene, where we have the conduction and valence bands that are degenerate at the high symmetry K and K prime points, the so-called Dirac points, where the bands disperse linearly. And as a result, the electrons are described by a 2D massless Dirac Hamiltonian. And this is what gives rise to many of graphene's remarkable properties. And this unique band structure is by no means an accident, and in fact is a direct consequence of the underlying symmetries of graphene. So the combination of time reversal symmetry and inversion symmetry locally stabilizes the Dirac points, this contact point. A gap cannot open up if you preserve these symmetries, at least locally. And then the free-fold rotational symmetry, the C-free symmetry, pins the Dirac points at the high symmetry points. So let's see what happens when we strain the lattice. And here we can see that the hopping parameters now become anisotropic. And as a result, we break the threefold rotational symmetry. And as a result of this, the Dirac cones decouple from the high symmetry points and shift in momentum space. And this shifting of the dispersion in momentum space is effectively described by a gauge field-like term in the Hamiltonian. And this so-called pseudo-vector potential depends on how you strain the lattice through the strain tensor epsilon. Now, this is the case for uniform strain, but if we want to generate a pseudomagnetic field, we have to remember that this is given by the curl of the vector potential. Therefore, we have to have a strain tensor which also varies with position. In other words, we have to break the periodicity of the structure in order to generate a pseudomagnetic field. Now, this phenomenon is not restricted to the physics of graphene, and in fact can be emulated in any system that emulates that shares the same underlying symmetries. So, for example, several years ago, Motysegiev's group demonstrated these pseudomagnetic fields in so-called photonic graphene, which is essentially a honeycomb array of evanescently coupled waveguides. And this system essentially simulates the type binding physics of graphene. So you have hopping of photons between neighboring waveguides due to the overlap of the evanescent field. And because they have meticulous control over the lattice sites, they engineered perfect trigonal strain patterns into the lattice, which gives rise to a uniform pseudomagnetic field, which points normal to the plane of the lattice. Now, the main drawback of this approach is that the pseudomagnetic field is usually fixed by the strain configuration that you imprint into the lattice design. So for example, in this work, in order to change the pseudomagnetic field, they had to redesign and fabricate a new structure with a different strain pattern. And the strain patterns that you require are very precise. So this limitation raised a few interesting questions for us. So first of all, can we find some other mechanism, some other route to tuning these pseudomagnetic fields without having to reconfigure the entire lattice? And secondly, and more interestingly from my point of view, is can we find a way of switching off the pseudomagnetic field without having to remove the strain? Now, from the intuition that we've built up from the type binding models, this seems impossible, because if we distort the lattice in any way, we change the hopping parameters, and inevitably we get a shift of the Dirac cone. But at least in principle, this tunability is possible, because while we need to break the C-free symmetry of the lattice to have a gauge field-like term emerging in the Hamiltonian, the symmetry tells you nothing about the magnitude of this term. So it could be 0. But this depends on the specific details of the system. So if we want to have this tunability, we have to move away from simulating type binding physics, and in particular find a way of modifying the nature of the interactions between the lattice sites. And we can do this with metasurfaces. So in this work, we consider a minimal model of a honeycomb metasurface, which is just an array of interacting dipole emitters or antennas, with subwavelength nearest neighbor separation, such that the metasurface supports surface polaritons which are evanescently bound to the lattice. We also, for simplicity, just assume dipole moments that are oriented normal to the plane of the lattice. Now, the collective dynamics of this system is just described by a coupled dipole model, but it's well known that the radiative properties of emitters and antennas is not entirely determined by their intrinsic properties, but they also depend qualitatively on the surrounding electromagnetic environment. So we exploit this by embedding the metasurface inside of a cavity waveguide, and this allows us to modify the Green's function, which in turn allows us to modify the nature of the interactions between the dipoles. To elucidate this a bit further, we can decompose the Green's function into its longitudinal and transverse components, where the longitudinal component describes the short-range Coulomb interactions, and the real part of the transverse Green's function describes coherent interactions which are mediated by the cavity photons. And these tend to be long-range in nature, as shown here. Now, it's tempting to assume, because we have subwavelength nearest neighbor separation, that the near-field Coulomb interactions dominate the physics. Now, this is true for free space and for relatively large cavity widths, as shown by the blue lines here. But for small cavity widths, shown by the orange lines, you can see that the Coulomb interactions become exponentially suppressed for small cavity widths. And this is due to the screening effect of the cavity waveguide. In contrast, the photon-mediated interactions become more dominant. And this is because of the reducing mode volume as you reduce the size of the cavity. So you can see that just by changing the width of the cavity, we can tune the dominant dipolar coupling between short-range Coulomb interactions and long-range photon-mediated interactions. Okay, using these coupled dipole equations, we have derived analytically an effective Hamiltonian that describes the polaritons. So we have an effective Dirac Hamiltonian, and then these strain-induced pseudo-gauge fields. So we have a pseudo-vector potential A and also a pseudo-scalar potential phi. Now, the form of these pseudo-gauge fields are exactly what we find in graphene and artificial graphene systems, because they're constrained by the symmetry. But in this case, the coefficients A0 and phi0 have a very non-trivial dependence on the cavity width. So here I show how these parameters vary as we reduce the cavity width. And the blue lines correspond to the contributions from the short-range Coulomb interactions, and the orange lines show the contributions from the long-range photon-mediated interactions. And you can see a few important points here. So first of all, they contribute with opposite signs, and therefore they're always in competition with one another. They're always trying to shift the Dirac cone in opposite directions. And secondly, for large cavity widths, the gauge fields are dominated by the Coulomb interactions, and for small cavity widths, the gauge fields are dominated by the photon-mediated interactions. So if we add the contributions together, there must exist critical cavity widths where these contributions perfectly vanish, and it switches off the pseudo gauge fields. So this is quite non-trivial. So what it's saying is that you embed a metasurface inside of a cavity, and if you apply strain, at least at this critical cavity width, then no gauge fields are generated. Okay, so let's try and look at some of the consequences of this tunability. So if we consider a strain configuration that generates a uniform pseudomagnetic field, then the effective Hamiltonian predicts that the Dirac cone splits into these quantized Plaraton-Landau levels, where the spectrum is given by this expression. Now, in previous studies, the spectrum is usually fixed by the strain configuration. But here, the Plaraton-Landau levels depend qualitatively on the surrounding electromagnetic environment. So we can drastically reconfigure the Plaraton-Landau level spectrum just by changing the cavity width. And specifically, the transition from Coulomb interactions to photon-mediated interactions is accompanied by this collapse and subsequent revival of the Plaraton-Landau levels. Now, in order to verify these analytical predictions, we also developed a full multiple scattering theory. And here we plot the spectral function for a dipole located at the center of the metasurface, which is just the imaginary part of the effective polarizability, which takes into account all of the multiple scattering events. And we're particularly interested in this so-called Dirac region, which corresponds to the Dirac cone part of the Plaraton spectrum. So this is for an unstrained metasurface with a relatively large cavity width where the Coulomb interactions are dominant. So let's see what happens when we strain the metasurface. What we see is emergence of a series of sharp resonant peaks, which do not emerge in the unstrained case. So these directly correspond to these strain-induced Plaraton-Landau levels. Now, this is, again, the spectral function for the same metasurface, but now for critical cavity width, where we predict that the pseudomagnetic field is switched off. This is the unstrained case. If we now strain the metasurface, remarkably, we see no Landau levels emerge in the Dirac region. And in fact, there's very little qualitative difference between the strained and unstrained cases here. So it's a direct evidence that the pseudomagnetic field really is switched off at this critical cavity width. And then finally, here is a spectral function, again, for the same metasurface, but now a very small cavity width where the photon-mediated interactions are dominant. And when we strain the metasurface, again, we see the emergence of a series of resonant peaks, which directly correspond to the Plaraton-Landau levels. So this verifies that the collapse and revival of the Plaraton-Landau levels, which is induced by the cavity waveguide. So just to quickly summarize, what I've tried to highlight is that while the symmetry determines the form of the Hamiltonian and the form of the pseudomagnetic gauge fields, it's the interactions that depend the strength of that dictate the strength of the pseudomagnetic field in the metasurface, and we can exploit this by manipulating the surrounding photonic environment. So this also leads to some interesting questions. For example, how does this theory generalize to more complex antennas, such as split ring resonators and dielectric Mie resonators, which are prevalent in metamaterials research? And also, are there other ways of modifying the interactions by engineering different structured photonic environments? So, for example, embedding emitters in photonic crystals or mediating interactions with surface plasmons, etc. And also led to another interesting question, which we explored, is can you induce topological transitions using this method? And in a recent paper, which we've recently put on the archive, we have shown that you can indeed induce topological transitions as well. And just by changing the cavity width, you can switch the chirality of the topological edge states. So with that, I would like to say thank you for your attention and invite any questions.
Excellent talk, Charlie. Thank you so much. So we do have one question in the chat right now. The first question is, rather than use strain to modify the metasurface, would it be possible for one to use the dielectric environment, varying it in space to achieve a similar end to varying strain in space? Yeah, that's what it
yes.
says.
In principle, yes. You essentially need to be able to smoothly break the C-free symmetry. That's a requirement. So whether you do that through the lattice sites or the environment, I think it should give rise to a similar effect. Yeah.
Great. And so I was kind of wondering, are there any radiant Landau level states as well, or?
Yeah, that's quite interesting. So we obviously consider sub-wavelength separation. So all of the plutons are subradiant and exist beyond the light cone. Whether or not these can exist inside the light cone is a good question, because if they just radiate, if they're leaky waves, then the Landau level peaks are just going to be broadened. So it's difficult to see how you could have these sharp resonances unless there's some kind of bound state in a continuum. So it's definitely an interesting question, but I'm not sure if it's been done yet.
Okay, thanks. And then I think we have time for one more question. Let's see. Can you articulate one more time, like what are the lengths of the cavity, or like the displacement that you take to turn it on and off?
So let's see if I can go back. So for this minimal model, again, we don't specialize to a particular realization. So we take point dipoles, and essentially for this system, the cavity width has to be smaller than the resonant wavelength in order to have a significant effect on the interactions between the dipoles. So for example, on the right-hand side, this could be a cavity width of on the order of the spacing between the dipoles. But I don't think that's a strict requirement, but it's more of a feature of the minimal model that we have, because when you have finite, say, meta-atoms, then the cavity is going to have a far bigger effect because it comes near to the finite size meta-atom is going to modify the resonant frequency and modify the interactions. So I don't think it's a strict requirement. It's more of a feature of the minimal model.
Great, excellent. Well, thanks again for your wonderful talk, and yeah.
Okay, thank you.
So our next presenter is Nolan Lasseline from ETH Zurich. Nolan, go ahead.
Okay, can you see everything? Okay.
Yes, I can see.
Wait, and now I go to presenter view. Now it should be good. Yes.
Yes.
Okay. Yes. Hello, everybody. Good evening from Zurich, and thank you to the Photonics Online Meetup Committee for having me here to present today. And what I'm going to talk about is some new work that our group fairly recently came out with just a few months ago, which we call optical Fourier surfaces, as you can see here. And so being in the Metasurfaces session, sort of the common ground with a lot of the things that you're seeing today is that we are manipulating light with structured surfaces. And of course, this is something that humans have been interested in doing for a very long time. And in these two lenses that I show you here for this example, they're actually very different, but interestingly, they do have something in common. And that is that their function and performance, so what they do and how well they do it, are determined by their surface profile. And of course, nowadays, modern research is exploiting complex nanostructured surfaces to achieve these new functionalities. And this falls into the very broad class of diffractive optics. And these are things like metasurfaces, gratings, and holograms. And already we see that there's a very broad range of applications for these diffractive optics. So let's just take a quick look at that overview. And so for these various applications, we can sort of categorize them a bit into what they're doing. The first one being something we can call free space diffraction. And these are things like spectroscopic gratings or metasurfaces, where essentially we take photons from free space, they impinge on the structured surface, and then they diffract either to disperse or to form some type of image or focusing. The second general function is that of guided mode diffraction. And these are things like silicon photonic grating couplers or plasmonic grating couplers, where essentially we shine light onto a grating coupler from free space and it couples into a wave guided mode or vice versa. And finally, there are some functions that are happening completely on chip without the free space part. And so these can be things like photonic crystals and distributed feedback lasers, where you have a periodic structure in the surface plane, and the sort of action that they are having on the photons is completely in plane on your chip. And I think it's pretty obvious from this sort of slide that there are a very broad range of applications that these diffractive optics can have. And then this sort of poses the question, can we understand these very different functionalities with a simple and general common framework? And we can very easily within the wavy world of Fourier optics. And so Fourier optics is essentially the study of optical phenomena using Fourier transforms. And this allows us to decompose very complex problems into just a simple sum of waves. And so, for example, if we take one of those diffraction gratings, which I just showed in one dimension, what we can do is we can write down the inverse Fourier transform, which relates on the left our surface profile in real space, f of x, to its spatial Fourier spectrum, f of g, in frequency space on the right. And it's actually here in frequency space with which we can design and understand the diffractive properties of our elements. And this has been known for a very long time, and mathematically this is very beautiful and very simple. But in reality, we actually have this problem. And that is when you look at real gratings that we make in the lab, they're not wavy, but very often they have these sort of square profiles that we see here. And ultimately what this means is that these diffraction gratings, instead of having sort of a single periodicity, which we often think about them as having, they actually have a mathematical sum of many, many periodicities, shown again in the left on real space and in their Fourier spectrum on the right here in frequency space. And ultimately, this leads to two issues. And the first is that we have many of these unwanted spatial frequencies that you see here, and this contributes to loss in the diffraction. And furthermore, we can't freely add spatial frequencies that we might want to. And so this is posing limitations on the function of these diffractive optics. And ultimately, this is limiting their capabilities. And what would be really ideal would just be to have the ability to make wavy surfaces. And so here we introduce a way with which we can do that, which we call optical Fourier surfaces. And we do this by starting with very simple analytical design. So in this case here, sort of our most basic element is just a sine wave in one dimension. And what we do is we take this analytical function and we can convert it into a grayscale bitmap shown below. Then we use a technique known as thermal scanning probe lithography, or commercially known as the nanofraser. And we take this grayscale bitmap and we sort of directly pattern it into a polymer surface on our sample shown here. And then in our group, we use a process known as template stripping to transfer this to an optical material. In this case, silver, we're going to take a look at, where we just evaporate silver onto our template. We apply glue to the back of it, and then we strip it off. And this yields our wavy diffractive surfaces in the final optical material we care about. So again, in this case, silver. And what's really nice is when we do this, we can see that the surface profile has a very low RMS error value. So in this case, its error is only 1.8 nanometers compared to the function that we were trying to pattern. So it shows the accuracy of this approach. And now that we can produce these surfaces, the question becomes, how do we optically characterize them or measure their performance? And so we do this with a reflectivity measurement, and we do this by looking at how photons couple to surface plasmon polaritons along this metal surface. And so if we take this Fourier surface that I showed in the previous slide, so this single sine wave shown here, we have its Fourier spectrum down here in the inset, and just below, this is the measured surface profile with atomic force microscopy, where the blue circles are the measured data points, and the blue line is the desired function that we wanted to pattern. And then we do a reflectivity measurement in K-space. And so this is what I show down here. And so on the y-axis, we're sending in a broadband light source. So essentially over the whole visible, where we show the wavelength or the photon energy on the y-axis. And the x-axis, we plot the in-plane wave vector, which is related to the angle of incidence. And then we're doing a reflectivity measurement. So for every point on this map, we're looking at how much light is reflected, or how much essentially comes back to us. And where it's dark, we see that 100% of the light is reflected. And where we have this sort of orange band here, that shows that we have a dip in reflectivity. And we attribute this dip in reflectivity to diffractive coupling between our incident free space photons and surface plasmon polaritons, which then propagate away along the surface and don't return. And finally, on the left, we show our experimental optical data. And on the right, we show a calculation from a simple analytical model we have. And we see a very good agreement between the two. And so this confirms that it works, that we can use these sine waves as sort of our basic building block. And then what we can do is we can freely add them together to achieve a desired optical response. And so, for example, the next step in complexity that we could take is to do the same thing as on the left, but now with two sine waves, as I show here. And again, when we look at the optical data, what we very nicely see is that these orange bands, again, corresponding to diffractive coupling of photons to SPPs, are doubled. So we essentially have two sets of these bands because we now have two sine waves in our surface profile. And of course, we can increase the complexity as much as we like. So here I show it with 3 sine waves with some particularly higher spatial frequencies this time. And even through all of this visual complexity, again, what we very nicely see when we do our optical measurement is that we have optical data, which very nice confirms the expectations from our analytical model. And this particular surface was shown here, or was chosen here to have these 2 stop bands or band gaps, which I will elaborate a little bit more on in a couple slides. And so I think now would be a good point to sort of stop and ask the very obvious question, okay, but how does this compare to traditional gratings that we've had for quite some time? And so a way that we can make a direct experimental comparison is we can take these analytical functions, which I just showed you, and we can convert them to a 2-level profile just based on a thresholding technique. And just to show you that this is like a relevant way to do it, the FEISS group here at ETH, they have employed this function to make distributed feedback lasers for multiple wavelengths. And so when we do this process, then we can fabricate these gratings using standard techniques, so electron beam lithography and etching. And when we do this, we end up with gratings that look like this. So on the left in blue are the Fourier surfaces that I showed previously, and on the right are their binarized versions, again measured with AFM. And you can clearly see that a lot of the content that is contained in these wavy surfaces is sort of lost when we convert to the binary. And then it should be no surprise that when we shine light on these and we do the same optical measurements that we did before, we see that the optical response is strongly corrupted by the fact that we're no longer working with this nice wavy basis. And again, on the left is the same data as I showed you previously, and on the right is the data from the binary versions. And so what this sort of directly confirms is that with our approach in these wavy surfaces, we can precisely manipulate these electromagnetic signals. And then it, of course, begs the question, what else can we do with this? And so just to show some examples here, the first one, I'll start by revisiting these stop bands, which are important for a number of applications. And so what we can do for these stop bands is we can write out a surface profile here, where this amplitude of the second component, A2, is responsible for opening up this stop band. And so what we can do is fabricate a series of gratings where we tune this A2 from 0 to 25 nanometers. And when we do this, I show these grating profiles here in GIF format, so we can see sort of how the grating profile is evolving as this A2 grows. And what we very nicely see is when we take this optical data, we see that the width of the stop band, which is directly related again to this A2 parameter, is nicely opening and closing as this A2 parameter becomes larger and smaller, as shown in this format here. And so this, again, very nicely confirms mathematically that we have sort of our hands on all these tuning knobs and we can really precisely structure these surfaces for a desired optical response. And until now, this has all been done with sine waves modulated in 1 dimension, so along X as I've shown, but we know that surfaces are 2D, so can we sort of expand these capabilities beyond just this 1 dimension? And of course, we can do this and we can look at some interesting symmetries that arise. And so just to start with a basic example, if we take 3 sine waves rotated in the plane by 60 degrees relative to each other, shown here, overlaid on the topography, we can create essentially a hexagonal sinusoidal crystal, which exhibits 6-fold rotational symmetry. And then we can transfer this pattern to a metallic surface and we can shine light on it and look at the diffraction pattern. And again, these are reflectivity measurements. Again, on the x-axis, we plot kx, but now on the y-axis, we're plotting ky. So basically a 2D k-space image. And again, what we nicely see is that we have these reflectivity dips corresponding to diffractive coupling to SPPs. And these reflectivity dips very nicely overlay with the expectations from our analytical model, which is shown with this these white dashed lines here. And so now for this structure, we might ask ourselves, what about the rotational symmetry? And we'll find out that this 6-fold is actually the highest possible for a periodic structure. So can we increase it somehow? And the answer is actually, yes, we can. And all we have to do is choose the appropriate combination of sine waves with the angular separation in between them. So for example, if we do this here for 6 sine waves separated by these 30 degrees, we actually end up with a quasi-crystalline pattern. And this has 12-fold rotational symmetry, and it has the interesting property of being quasi-periodic and no longer periodic. And this means that while it has this high rotational symmetry, it no longer possesses translational symmetry throughout the crystal. And then, of course, we can transfer this to our optical material. And when we do our reflectivity measurement again, we very nicely see that the 12-fold rotational symmetry contained in the surface profile is reflected in the rotational symmetry of our diffraction pattern that we measure optically. And again, it very nicely matches the expectations from our analytical model. And at this point, I think it gets perhaps a little bit abstract. And so just to sort of bring it back to earth here, we can ask the focus question. So what about some practical applications of these Fourier surfaces? And so for these applications at the beginning, I told you that square gratings had these two issues listed below. And now we have these wavy Fourier surfaces, and we don't have these limitations anymore. And so this would imply that we should be able to do two things. We should be able to make high efficiency diffraction gratings, and we should be able to now implement some new functionality that can solve an existing problem that wasn't able to be solved before. And so we can start with the high efficiency gratings. And the way that we measure these is we simply shine light on these gratings at normal incidence, shown here with Ki, and we look at the intensity of light that is diffracting into the 0 and the plus and minus 1 orders here. And just note that now we are diffracting to free space, and as I mentioned at the beginning, that is different than the plasmonic coupling that I was showing before, but otherwise it's still essentially the same thing. And so now when we shine this light on a sort of left-right symmetric sine wave, as I show here, and now it's quite a bit deeper than the previous ones, we can trace out these diffraction efficiency curves to see how the surface is responding. And so again, with this color code of red and green, we can trace the diffraction efficiency. So this is what I plot on Y here as a function of wavelength when we're sweeping this wavelength. And what we see is that for the plus and minus 1 orders, we have essentially the same intensity that is diffracting there because it's symmetric. And these each have roughly 50% intensity. And so when we sum these two up, we get this sort of overall diffraction efficiency of the surface of nearly 100%. But of course, for many applications, we're not interested in the symmetric diffraction, but we would actually like to break the symmetry and send all of our light into just one diffraction order, plus 1, for example. And so what we can do is similar to a Blaise grating, we can make a Fourier series, which is just the first two components of a sawtooth, an asymmetric sawtooth profile. And we can shine light on this and now see how it behaves. And what we nicely see is, compared to the case on the left, we are now diffracting essentially all of our light, so with nearly unity efficiency, into the plus 1 diffraction order. And the light that previously diffracted into minus 1 is now suppressed towards 0, shown in green. And so finally, so this of course shows we can make efficient gratings and we can steer the light in the direction we would like. And so finally, let's take a look at some new functionality. And so the problem we'll examine is that of multi-wavelength coupling. And so in this paper here, they nicely make a compact sort of waveguide integrated hologram. And what they do is they couple red, green, and blue lasers into their waveguide, which then they diffract from this outgoing grating to make their hologram. And the thing is, because they use a traditional grating with sort of a single periodicity, there's this angular dependence for all of these three colors, which takes this very nicely compacted device, and it sort of poses this frustrating limitation on the design of the optics to make it work. And so this is frustrating, and this is what we would like to eliminate. And so the cartoon of what we would want shows the situation here, where we want to come in the same angle of red, green, and blue. And we know from now our Fourier analysis that we simply need a spatial frequency corresponding to each color. And this produces such a grating shown here. And when we shine light over the entire visible range, all at normal incidence, what we very nicely see are these three prominent reflectivity dips, which correspond to the coupling of red, green, and blue photons, all at normal incidence. And ultimately what this shows is that these Fourier surfaces are mostly a very simple, but also a very powerful approach to solve some problems that exist in photonics. And then with that, I'll just quickly conclude. So we introduced here Fourier surfaces, these wavy diffractive surfaces. We use them to generate some improved diffractive optical elements. And I think most importantly, this opens up a lot of exciting new possibilities, not only for metasurfaces, but for optics in general. And finally, I would like to thank my co-authors listed here in bold and some other people below who helped me along the way. And I would like to thank you all for your attention. And I will now open up for any questions you may have.
Thanks, Nolan. What a great talk.
Thank you.
Let's see what the Q&A has. So I'll start at the bottom. We have a question from Pavel Shaptarenka, and it says, excellent talk, thanks. Perhaps building off of, they're building off of a previous question. Let me start with the first question then. Okay. So we see that it says, you've shown incredible control, but only for reflective surfaces. Is there any insight on how to extend this to transmission?
Yeah, that's a great question. So of course, the first thing that you would need to do is you would need to have a material that in the wavelength range you're working has basically transmissive properties and it won't just reflect it. And so what I can just very quickly show you is we did this in a number of materials. I only showed silver here for simplicity, but for example, if you look at the top right, we also did this transferring these to titanium dioxide, and this was done on a completely transparent substrate. And so if you do this process for the correct material, again, in this case, TiO2, you could also do this for transmissive surfaces, yes.
Oh, great. So jumping on to the next question, it asks, how straightforward is translating the surface into various dielectrics? Well, I guess that kind of solves it, right? I think you explained that just now.
Yeah.
So another question is, what's the largest angle you can tilt to? Does this correspond to the feature size?
I don't completely understand the largest angle you can tilt. Like of the substrate in an experiment, I guess you would, that means, or?
I think they mean like, what's the largest angle you could tilt the...
Like that you could diffract the outgoing beam to, is that?
That might be it, maybe.
Yeah. Okay, so if I assume that the largest angle means, what is the largest angle at which you can diffract? Maybe I can just use this cartoon here as a prop. So basically, the angle at which your outgoing light diffracts to depends on the wavelength of the light and the spatial frequency of your grating. And what we're showing here is that basically, we choose a spatial frequency such that we the outgoing light comes away at an angle that we can collect with our microscope, and then we can sort of quantify the intensity in that order. But in all of the plasmonic cases we showed before, in a way, that is kind of like a 90-degree angle where we diffractively couple to an in-plane mode, which propagates away along our surface. So you are sort of free to sweep that wavelength, or sorry, that angular range, dependent on your wavelength and your spatial frequency, sort of anywhere that you can have photons, or in the case of guided modes, wherever guided mode can exist in your material, I would say. I hope that answers the question.
Great, thanks. And I think we have time for one more question. It's from Amit Agrawal, and it says, could you speak to scaling these optics to the centimeter scale?
Yeah, that's a really good question, and that's probably the biggest challenge that we have laying in front of us with these type of surfaces. So the limiting factor of how big we can make these surfaces is sort of twofold. So the first is within one patterning process, how big of a field can we make? And this is dependent on the piezo stage of our thermal scanning probe. So we have the probe on the stage, and it has a particular range. Now, this range is about 50 by 50 micrometers, so certainly smaller than this centimeter scale that the questioner asks. But there is no upper limit to how many of these fields that we can do in parallel beside each other and that we can stitch together. Of course, at some point, this will take longer to scale these up to a larger area. And there are perhaps some technical difficulties with how accurately can you stitch it for many of them put together. But this is something that we are looking at pursuing, and something, of course, for many applications that we need to look into. And the final point is that one of the biggest reasons that we chose to exploit templating to make these surfaces is because in the end, it doesn't matter how long it takes to make a template. As long as you make one good template, you can use processes such as imprint lithography or the templating that we show, and you can constantly and sort of faithfully reproduce many copies with the same surface without using very much time. So yeah, that's something we're looking into.
Excellent. Thank you. Well, that's about all the time we have for today. And I appreciate you taking the time to present today. Thanks. So our final presenter for this session is Lu Chen from the National Institutes of Standards and Technology. Dr. Lu Chen. And please remember to enter your questions into the chat anytime during the presentation. All right, Dr. Chen, take it.
Thank you for the introduction. And thank you for this opportunity to present on this fantastic online platform. The tutorial and the talks earlier in this session have already given a fantastic introduction on metasurfaces. So today I'd like to show how metasurfaces can also control the temporal waveform of ultrafast pulses. So ultrafast pulses are the shortest artificial events ever generated and have been widely used to study extremely fast phenomena in nature that would otherwise be inaccessible. So we work with femtosecond pulses. That's 10 to the negative 15 seconds. So this is the time scale that we're talking about today. So the pulses are generated by a multi-octet Sapphire oscillator, which generates a train of short pulses in the time domain. The pulse width is only 7 femtoseconds. And in the frequency domain, each pulse contains millions of equally separated frequency lines covering a very broad bandwidth. For a 7 femtosecond pulse, the bandwidth is 200 nanometers. I just want to echo that the time domain and the frequency domain can be transformed to one another by doing Fourier transform. So in principle, to shape an ultra-fast pulse, we can either directly modulate in the time domain or change the frequency domain, which by Fourier transform will also shape the temporal waveform. The latter here is actually much more practical because there is no modulator fast enough to directly manipulate on the femtosecond timescales. So what pulse shaping really means is to control the phase, amplitude, and polarization of each frequency line. The ability to shape an ultra-fast pulse, most commonly its phase and amplitude, basically a scalar waveform, has led to numerous advances in modern science and technology. One application that forms the backbone of high-field physics and was awarded the 2018 Nobel Prize is the chirped pulse amplification. So the pulse is first stretched by manipulating its quadratic phase, spectral quadratic phase, then amplified and finally recompressed to generate extremely high peak intensities. Adding amplitude control makes the pulse shaping more comprehensive. So independent phase and amplitude control allows generation of nearly arbitrarily shaped scalar waveforms. For example, this is a pulse multiplication. The input is a train of pulses that are separated by the repetition rate, which basically is determined by the laser cavity dimension. So by applying a phase and amplitude modulation, the output now has a much higher repetition rate. In addition, light field is actually a three-dimensional vector. So being able to further shape the polarization degree of freedom brings chirality into the picture. And there are many applications that can be enabled by the temporal polarization shaping. For example, spatial temporal control of nano-optical excitations, where a polarization shaped pulse can locally switch the near field distribution in the vicinity of a nanostructure, or force molecular rotation using the technique of optical centrifuge. So here the light polarization continuously changes with an increase in rotation speed, or in this case, selective production of enantiomers from chiral molecules. So as explained earlier, we use a Fourier transform pulse shaper. A grating and a parabolic mirror perform the optical Fourier transform, separating and focusing different frequencies at different locations. A Metasurface is positioned in the focal plane to provide a complex masking function to manipulate the spectral features. And the way we do that is, so this is a top view of the Metasurface. We group the nanopillars into superpixels to address a set of frequency lines. And then another mirror and grating recombines to shape the frequencies into output pulse. The Metasurface here offers many advantages, including high spectral resolution. So one big challenge when it comes to shaping ultra-fast pulse is to cover such a broad bandwidth while still maintain a high spectral resolution. So here is a picture of our Metasurface devices. Each line here is one Metasurface. It's about 2.2 centimeters long, and we divide it into 660 superpixels to cover a 200 nanometer spectral bandwidth. And here is a SEM image showing the nanopillars in 2 adjacent superpixels. There are other advantages like multifunctionalities at the single pixel level, which we will also explore later in this presentation. So using this approach, we have already demonstrated simultaneous and independent control of the phase and amplitude of a linearly polarized pulse, basically scalar pulse shaping, achieving operations like pulse compression, where we compensate and recompress a pulse back to its transform limited width, and high order distortion by adding a designed third order dispersion to the input pulse to generate those wiggles, and also pulse splitting. So here a single input pulse is split into two replicas separated by a design time delay. So so far we have shown that metasurfaces can shape the scalar waveform of a femtosecond pulse. Next, I'd like to show how we can also control the temporal degree of freedom to achieve vector pulse shaping. So the design principle is explained by the Jones calculus. The input pulse is linearly polarized along the horizontal direction. Here we assume a Gaussian envelope. The metasurface itself can be explained by an anisotropic wave plate. So theta is the rotation angle of the nanopillar. Here we set theta to be 45 degrees. And phi x and phi y are the propagation phase along x and y directions. So after the calculation, the output polarization state is controlled by this propagation phase phi x and phi y. And this propagation phase comes from the fact that when light propagates through the nanopillar, it acquires an additional phase due to propagation. And this phase, the amount of this phase change is determined by the light frequency as well as the nanopillar dimension. So by controlling the lateral sides along x and y directions, we can design different phi x and phi y functions at different frequencies. And the temporal waveform of the output pulse is the Fourier transform of the shaped frequencies. So by properly designing phi x and phi y functions, we can design all kinds of different pulse shapings. For example, this is one possible polarization twisted pulse. The axes are time, P and S polarizations. So basically, this is a three-dimensional electric field representation. The orange and cyan projections are the electric field amplitude for P and S polarizations respectively. The gray curve on the surface tracks the tip of the electric field vector. And we also have a color-coded Poincare sphere showing the temporal evolution of these polarization states. The colors represent time delay here. So a Poincare sphere is a graphical representation of the Stokes parameters, or in other words, the polarization states are represented by points on the surface of the sphere. For example, any point along the equator represents a state of linear polarization, with the directions being horizontal here, 45 degrees, 90 degrees, which is vertically polarized, and 135 degrees. The north pole represents right circular polarization, and the south pole is for left circular polarization. And any points in between are elliptically polarized. So here are our experimental results. From spectral interferometry, we can extract the spectral phase and the intensity for the P and S polarized components. And the experimental values match the design curves pretty well. And the temporal waveform of our measured output pulse is shown here. So the pulse starts with a polarization here at negative time delay, gradually approaches to a right circular polarization, then elliptical polarizations, then cross the linear polarization around time delay 0, then back to elliptical polarizations, but with an opposite handedness, and then finally reaches for a left circular polarization, all within the pulse itself. We can also achieve other types of polarization shaping by simply choosing a different design for the phi x and phi y functions. For example, here shows a set of twisted linear polarizations as a function of time. which are represented by the points on the equator here. And another pulse that follows a different circular path on the Poincare sphere, changing from right to left, then back to right circular polarizations. So far, we have shown that metasurfaces can shape the temporal profile of a femtosecond pulse, both scalarly or vectorial waveforms. The spatial wavefront so far has always been a Gaussian beam. So a Gaussian beam in, then a Gaussian beam out, but with a different temporal waveform. So one of the advantages of dielectric metasurfaces that we briefly mentioned earlier is the multifunctionalities at the single pixel level. So we also explore this property to show simultaneous spatial and temporal pulse shaping. So the idea is to superimpose a secondary two-dimensional phase function within each superpixel. So for example, a vertex spatial structure can be added to the temporal varying polarization by superimposing a spiral phase to phi-x and phi-y functions. What we would expect then is temporally, this is a polarization twisted pulse, and spatially we have a vertex beam. I'll just show some initial results as a proof of concept. Here we designed a vertex beam that carries a topological charge of 1. The design phase topography for phi-x and phi-y for the first 10 superpixels are shown here. In this design, we divide the entire spectrum into 200 superpixels. I'm only showing the first 10 due to limited space. So each superpixel has a spiral phase for the spatial shaping and an effective phase for the temporal shaping. And the bottom figure is an optical reflection image of our fabricated sample, also just showing the same first 10 superpixels. We also measure the interference pattern at one of the spectral components using a CW laser at 785 nanometers. And the interference fork confirms that the spiral phase can generate a vertex beam of charge 1 at this wavelength. So I hope I've demonstrated that the metasurface's versatility in shaping a large bandwidth near infrared femtosecond pulse, and its potential in simultaneously shaping the spatial and temporal degree of freedom using the single pixel multifunctionalities. There are still many opportunities out there, for example, in nonlinear optics, active transduction, and coherent control. So I'd like to acknowledge my colleagues, our collaborators, and my advisor who made this work possible, and thank NIST and University of Maryland for their support. And with that, thank you very much for your attention.
Great. Excellent talk, Lu Chen. Thank you.
Thank you.
So we're going to turn it over to questions. And there's one in the Q&A that says, what material is the metasurface made of, and what is the damage threshold?
Oh, that's a great question. Let me see if I have a slide for that. So the metasurfaces are made from silicon nanopillars on quartz substrates. The damage threshold is actually one of the advantages. Oh, sorry, not this one. Anyway, so our metasurfaces are made from all dielectric materials, which means the damage threshold is much higher compared to, for example, liquid crystals in spatial light modulators. So it has a great potential in like high energy pulses or high field physics. I don't have the exact number here, but it might be in the science paper we recently published.
No problem. Thank you. So I have another question for you. Is there some way that you're showing that you can do all these polarizations as they pass through in a single pulse? And so is it possible that you could do some kind of full Stokes polarimetry with a single shot? Is that feasible?
Yeah, that's another great question. Thank you. So the way we characterize our pulse is similar to when we shape it, because it's on femtosecond scales. So the way we characterize that is by directly measuring the spectral phase and intensity and construct the electric field in frequency domain. And then by doing Fourier transform, reconstruct the temporal waveform. So that's how we measure this. I guess it's a different way compared to measuring CW lasers.
I see. Nice. Thank you. And have you done any interactions with like chiral structures or probed any chiral structures in potentially biological samples as well?
We'd like to. So with the polarization shift pulses, now we have the temporal polarization degree of freedom added. So in principle, any molecules or materials that have an intrinsic anisotropy or chirality on the femtosecond scales, now this information can be extracted. Of course, if anyone has any specific applications in mind that they think might benefit from this exotic pulses, we are always interested in other possibilities.
Excellent, thanks. And we have one more question from the audience. It says, would you expect high nonlinear effects due to the pulse interacting with the nanopillars?
Okay, that's another fantastic question, thank you. And that's the backup slide I had. So we did run the calculation, and the conclusion is we don't have any nonlinear effects. The reason is, first, the pulses are the wavelengths are separated along the x direction. So that's like different frequencies are on different locations. So and also by calculating the size of the focus for each superpixel and the pulse energy, what we get for the peak intensity is way lower than what would introduce nonlinear effects in silicon. So we do not consider nonlinear effects.
Okay, great, thanks. We have another question here. Have you explored or considered multi-material nanopillars?
Multi-material, that's definitely something we will be interested in. Yeah, we are not actively doing that, but we are looking into the possibilities of combining multiple layers in the nanopillars.
Great, excellent. Well, I think that's about all the time that we have for this session. Thanks again, Dr. Lu Chen, for your great presentation.
Thank you, everyone.
So I'd like to just wrap up this session and say thank you, everyone, for the great questions and participating in the chat. That concludes the Metasurface session. Please join us in an hour for the Biosensors session at 3:20. In the meantime, please join our virtual reality event on Gather. A link to this is included in the conference center, which was emailed to you with your registration. Thank you.
Hello all, welcome to the POM Biosensing session. I am Imran Chima, an assistant professor at Lahore University of Management Sciences, Pakistan. I want to thank my biosensor team comprising fantastic researchers, Dr. Tatwik Chalian, Rai University Brussels, Belgium, and Dr. Esin Sukulu, Montreal Clinical Research Institute, Canada, for their efforts in organizing the session. Before we get started, just a quick reminder to all of you to type your questions into the Q&A box throughout the talk and upvote the questions you think are more interesting. In this session, we have an exciting lineup of talks for you. We'll start with our plenary talk by Dr. Maria Soler, who is a senior researcher at Catalan Institute of Nanoscience and Nanotechnology, Spain. She is a recipient of various awards, including the Extraordinary Doctorate Award and the Pioneer Award. She is currently leading fabulous research for developing novel nanophotonic sensors for immunology-based diagnostics and personalized therapy applications for cancer and infectious diseases. Over to you, Maria.
Hi, hello. Okay, let me start presentation. Can you confirm that you see it?
Yes, we can see everything. You can go ahead.
Okay, thank you. So yeah, first of all, I would like to thank you for inviting me. Well, good evening from Barcelona. And just congratulations for this great meetup that you organized. So I would like to give an introductory section to our nanophotonic biosensors. And I will specifically talk about the work we are doing for COVID diagnostics. So first of all, I would like to introduce a bit our group. We are the Nanobiosensors and Bioanalytical Applications Group at ICN2 in Barcelona. We are led by Professor Laura Lechuga, who probably most of you will know. And as I said, we work with nanophotonic biosensors, but we put much effort in developing the applications for environmental and biomedical purposes. So we have a very multidisciplinary team. So we are physicists, we have engineers, chemists, biologists, and also even mathematicians and programming personnel. And I would like to remark here that being an engineering-based research group, most of us, we are women, which unfortunately this is a bit rare in our field. But let's go into the research. So for those of you that are not in the field, biosensor is an integrated device that is composed mainly of a transducer that is in close contact with a biorecognition element, such as antibodies or DNA probes. So when this bioreceptor captures or detects a specific analyte that is present in a sample, a series of physicochemical changes that occur in the transducer are readily transformed into readable signals. So for photonic transducers itself, what we measure is changes in the light properties, such as intensity, wavelength, or phase, for example. We specifically work in our group with evanescent field photonic biosensors. This evanescent field is a certain type of an electromagnetic field that occurs at the sensor surface and that penetrates with a decaying intensity on the dielectric medium where the biomolecular interaction occurs. The evanescent field is very sensitive to refractive index changes that occur at the sensor surface, such as a change of mass. That allows us to detect any biomolecular interaction in a label-free format and also in real time. The conventional sensitivities that we reach with this type of biosensors are between 10 to the minus 6 to 10 to the minus 8 refractive index units. And an asset of our biosensors is that it can be applied to virtually any type of analytes. It means proteins, nucleic acids, small molecules, peptides, or cells. Also, due to this simple operation procedure, these sensors have a high potential for integration in portable and in small devices that can be used at the point of care. So, in particular, in our group, we're working with two main type of biosensors. One's based on nanoplasmonics, surface plasmon resonance, and also with waveguide interferometers, in particular, our bimodal waveguide interferometer. So, this surface plasmon resonance is one of our simplest but most beloved technology, actually. We have several prototypes that we develop in-house, and we use them routinely in the lab to develop surface chemistry procedures, and also a lot of applications to diagnostics, to therapy, or to environmental control. Our sensor is not like the commercial Biacore device that most people know. Ours is small, is portable, the size is kind of a shoes box. We have 2 channels to work in parallel, and we also develop all the electronics and even customized software that we can use in the PC or also with a tablet. So we usually reach 10 to the -0 refractive index unit with our device. This translates into nanomolar to picomolar range for biomolecular assay. And as I said, yeah, we use it just every day for a lot of applications. But also in parallel, we also work with nanoplasmonics. This is nanostructured surfaces. We have investigated a lot of nanoplasmonic structures. Maybe most relevant are the nanoslits and these gold nanodiscs. We have developed and established a very cheap and simple nanofabrication protocol. So we can explore different sizes and geometries for the nanodisc to achieve the best performances. And the good thing is that we can employ these gold nanodisc sensors in very compact and simple devices, also user-friendly. We are developing as well a multiplexed biosensor device for these nanoplasmonic sensors. And this sensor, we expect it to be kind of the SPR prototype that I showed before. But our start in the laboratory is the bimodal waveguide biosensor. And this is an interferometric biosensor. It's similar to the well-known Mach-Zehnder interferometers or the Young interferometer. But the main difference is that we don't have the Y junction that splits the light into 2 different paths. Instead, what we have is a single planar waveguide that at the beginning, it only allows the fundamental mode of the light to travel. And then after a certain distance, there is a nanometric grid that excites the first mode of the light. So two modes, the fundamental and the first mode, travels along the waveguide till the output. The main thing here is that only the first mode of the light have an refractive, an electromagnetic field and an evanescent field that extends out to the surface of the chip. So it's the only one that is in contact with the sensor area. That means when a biomolecular interaction occurs on the sensor area, only the first mode of the light will sense this change of the refractive index, while the fundamental mode remains the same within the core of the waveguide. Then at the end, because of a phase change in the first mode, we will find an interference pattern that will be proportional to the change of the refractive index in the sensor surface. with this bimodal wave interferometer, we have reached outstanding sensitivities. We have reached between 10 to the -8 to 10 to the -9 refractive index units. This translates into femtomolar to attomolar concentrations of analytes. And also it is important that we work in the visible range using low power laser sources. And we fabricate our chips based on silicon microtechnology processes. So we believe that this type of devices have a very high potential for lab-on-a-chip integration and point-of-care biosensor devices development. And this is actually what we are doing. We are working in parallel in the whole engineering areas of the biosensor. So we work on the sensor chip fabrication, but also in developing polymer microfluidics and microfluidic cartridges for multiplexed detection. We also work a lot on the optimization of the surface functionalization, the packaging and storage of the chips after the biofunctionalization. And of course, we continuously try to improve and enhance the lighting coupling, the signal processing, and the automation of the whole device. So this is the technology that we proposed and we are using in the COMBAT project. That is what I would like to talk to you about. So the COMBAT project is an European project that we are leading, and it was granted in February last year, right when the pandemic started. So the COMBAT was as a response to the first European call for combating the COVID-19 pandemics. What we propose is to use these nanophotonic biosensors for rapid diagnostics and the surveillance of coronavirus. The project, as I said, we are the coordinators, but we collaborate with coronavirus experts, one of the most expert people in Europe. They are from Barcelona, from the University of Barcelona, from France, the University of Marseille, and also clinicians from Italy. That they are experts in the diagnostics of infectious diseases. So the main aim of COMBAT project, as I said, is to develop a biosensor for detecting rapid and with a high sensitivity the coronavirus, right? So our applications with this, of course, are the early diagnostics of patients and the population screening. But as a plus, we want to use it to monitor the evolution of different coronavirus in animals, so we can, in the future, prevent future pandemics or outbreaks. So what are we doing in COMBAT projects? Our idea is to use one single platform for all the analysis that may require. So the first approach is the direct virus detection. We want to detect the whole virus entities from respiratory fluids or saliva samples in a 15-minute assay. Our sensor will give us the highest sensitivity and also with a minimal invasive assay. And our plus here is that we can quantify the viral load in the patient. That means that if a patient has a high viral load, the clinician can manage it better and try to prevent serious symptomatology. The second approach is a PCR-free genomic analysis. For this, we target the viral RNA, and we plan it as a confirmatory test for an accurate diagnosis of SARS-CoV-2 infection. But also we want to implement this type of analysis as a multiplexed analysis. So we can discriminate in one single assay if a patient has COVID, has the flu, or has a common cold, for example. And this, as I said, we want to do it without PCR amplification, so the total assay time will be approximately 30 minutes, and we will not need any laboratory equipment. And finally, although it was not planned initially for the COMBAT project, we are also addressing the serological assays. This is the quantification of the antibodies that the patient generates in response to the infection. We think this is of extreme importance now, also not only for having an effective epidemiological studies that will help a lot by having a fast and accurate way to detect the antibodies, but also for vaccine evaluation and for controlling the immunity, the acquired immunity over long times. So I would like to show you, none of my results that I will present here are published yet, but I think it's worth to share it with all of you. So for the first approach, the direct virus detection, we plan it as a one-step assay. We select antibodies directed to the spike protein of the coronavirus and immobilize it on the sensor surface. Then we simply flow the sample over the sensor and we read the signal. For that, in the laboratory, we started working with a pseudovirus that is not infectious, just for our own safety, of course. And with this system, we check the affinity of the antibodies for the S proteins and also the specificity. We got a very high specificity with no crosstalk with other type of viruses. And the sensitivities that we got for the pseudovirus were in the range of 10 to 2 to 10 to 3 viruses per milliliter. These levels are more or less are comparable to the limits of detection that current PCRs in the hospital are achieving. So we are well positioned in this sensitivity test. Okay. And then just a few weeks ago, we received the real SARS-CoV-2 samples in our laboratory, and they were inactivated. They were inactivated through a UV treatment. And I wanted to mention that because a lot of people is using the thermal inactivation for the development of the assay. And we confirmed that by thermal inactivation, you completely destroy the virus structure. And this is not only reducing the sensitivity, as you can see in this graph. This is non-treated, this is treated at different temperatures, and this is with UV. So it reduces a lot the sensitivity of the assay, but also it may carry problems of reproducibility and reliability of the assay. So with these samples, what we are doing now is trying to optimize the assay, the real assay. And I can advance that the sensitivities that we are reaching are much better. Last week in the laboratory, they showed me that we are detecting a few tens of viruses in a sample. So we expect to start with the validation in clinical samples in the following month. And then for the next approach, I'd like to explain a bit how we plan to implement it. First of all, what we need to do is to select the viral genes that we want to target. And then we design a complementary DNA probe that we will immobilize on the sensor. And for the detection of the RNA, we will extract it from the virus. This is just breaking the virus. And we will go through a bit of, through a easy fragmentation procedure that can be done outside the lab. Then we flow this sample over the sensor, and the RNA of the virus will hybridize to the complementary probe. This capture of the viral RNA fragments will give us a signal. We trust in the high sensitivity of our device to be able to directly detect the specific viral RNA without the need of any preliminary amplification that will cost time and resources to the clinicians. So for now, what we did was a bioinformatics study to select the best regions of SARS-CoV-2 that will not crosstalk with any other pathogen or any other molecule that we may have in our body. We checked the affinities and the selectivity to detect this. This we did it with an SPR biosensor, and we reached a nanomolar concentration already. So when transferring it to the bimodal waveguide biosensor, we expect like at least 1 or 2 orders of magnitude better sensitivity. And what we plan to do, as I said before, is to implement this multiplexed biosensor. So what we are doing is detecting at the same time SARS-CoV-2 viral genes, but also influenza and human coronavirus. That's, as you see, on the external surface, they may be very similar, and especially for the human coronaviruses that are responsible for common cold, we may have problems of crosstalk when going to the S protein target, but not analyzing the virus genome. And also, what we will do with this approach is to do a multiplexed biosensor detecting whether they have beta coronavirus or alpha coronavirus, and that will allow us to monitor animal samples like bats or rodents and try to surveil them and detect early if there is a possible dangerous beta coronavirus that may create a future outbreak. So now to finalize the serological assay, the serological assay, for implementing it, what we did was selecting specific viral antigens, the N protein and the S protein of the virus, and functionalizing the surface with it. With that, we directly flow blood serum or plasma onto the sensor, and we will detect and quantify the specific antibodies that are present on it. We have reached very high sensitivities in the nanograms per milliliter range. This is actually 2 orders of magnitude below the required levels for the detection of antibodies. And we seen these very good results. We right away went to detect to evaluate clinical samples that we obtained from nearby hospitals. And as you can see here, this is just a few samples, but we could perfectly discriminate between COVID positive and COVID negative patients. So what we are doing now in the lab is much higher clinical validation samples, between 150 and 200 samples. And we are thinking of technology transfer actions, and that means, as you may know, to get funding for industrialization and commercialization of the sensors. And that's it. I'm not sure about the time. I may be very fast. But I want to finalize just thanking the COVID team in my group, that we have been working non-stop. Actually, since February, we did not stay at home for the harsh lockdowns. We continue to go to the laboratory and work on it. And also to thank all of you for your attention, and I will try to answer any question.
Thank you, Maria, for a really excellent talk. There are actually many questions here, and let's pick few questions in the interest of time. So the first question was on your biomodal waveguide design, where one of the attendees asked, what kind of laser did you use and what kind of detector, and how were you coupling the light in and out of the structure?
Yeah, so we are using just laser diodes. We work at 670 nanometers. So just with laser diodes, we can work. Also with helium neon that we had before, but we are trying to miniaturize everything. And as a detector, we are using just photodiodes and checking the intensity in 2 different regions for detecting this interference pattern. The coupling of the light is direct. We investigated some grating couplings, we investigated some vertical tapers and some other strategies. But right now, we just by approaching the laser diode, the fiber to the chip, it's directly coupled. And also the same with the detector, just placing the detector right out the light output, we can detect it.
So there is another question on the same design. Which is the microfluidic channel design you are using? Which is the flow and flush protocol? Do you need an external laboratory pump system, or you can integrate it into the instrumentation itself? And which is the liquid volume needed to perform a complete analysis?
Okay, so yeah, right now we are working with PDMS microfluidics that we develop ourselves in the laboratory. We have a few designs, one with bigger channels and one with smaller channels that we are trying to adapt to each waveguide, so 1 channel per waveguide, and in this way we will have up to 20 sensors per chip. And we are working right now, yes, with syringe pumpers and everything, but we have already done some work in collaboration with people at the RMIT in Melbourne, in Australia. And that we developed an automated microfluidics with specific valves and everything to have the buffer and injection valves all in the same optofluidic cartridge system. Okay, then I think the next question was the volume that we were needing. Right now, the sensor areas are for 15 nanoliters of volume. But this depends on the amount of sample that you choose. So the minimum will be this 15 nanoliter, but we currently employ between 50 and 100 microliters.
And let's move to your next design where you were looking at COVID virus. So the question is, great project, Maria, good luck. Do you know the dimensions of the binding sides of the virus? What is the longest dimension limit of the sensor surface?
Yeah, the sensor surface is, I think, 15 millimeters. So we will have more than enough room for a lot of sensors to attach there. These viruses are around 100 nanometers diameter, 100, 120. And antibodies are between 10 nanometers. So yes, we have a lot of room for them to attach.
Okay, so we have actually a lot of more questions, but we are out of time. So maybe you can respond to those questions in the Q&A session box. So once again, thank you, Maria, for this fabulous talk. And we'll look forward to seeing you again.
Thank you.
So reminding the audience throughout the talk, you can type your questions into the Q&A box. And then let's move to Italy now, where we have Federico Sala, who is a PhD student at the Department of Physics in Polytechnic University of Milan. And he's doing some exciting work on optofluidic biochips. So over to you, Federico. Thank you very much for coming.
Okay, thank you for the introduction. And I think I'm sharing my screen. If you can confirm that you are seeing my presentation.
Yes, we can see.
Perfect. So, good evening, everyone. I'm Sala Federico from Politecnico di Milano in Italy. And today I'm going to present to you my work on the integration of light sheet fluorescence microscopy on an optofluidic biochip. Okay. Perfect. So I will start with a brief introduction on the microscopy technique and its integration on chip. Afterwards, I will move on the microfabrication technique that we used to fabricate all our devices. And then I will focus on two different cases for two different types of samples. On one hand, single cells, and on the other hand, Drosophila embryos. I will end my presentation with conclusions and further perspectives of our work. Light sheet fluorescence microscopy is a particular type of microscopy technique in which you excite the fluorescence by shining the sample with a plane of light. The fluorescence emitted by the plane is collected by the detection objective orthogonally, plane by plane. By moving either the sample or the light sheet, you can scan through the whole volume and then obtain all the fluorescence from all the planes. This technique is inherently fast because you can acquire fluorescence plane by plane if compared, for instance, to confocal microscopy that acquire the fluorescence point by point. And then by stacking together all these planes, we can obtain a three-dimensional reconstruction. Moreover, it has low photodamage and low photobleaching since we are shining light only on the section of the sample that we are looking at. On the other hand, the complexity in the alignment of the light sheet and the mounting and the alignment of the sample can reduce the actual throughput of the technique. Our solution is the integration of light sheet directly on chip. So we start from a simple piece of glass where we can add a microfluidic system in order to continuously deliver the sample one after the other and to position them precisely onto the detection area. We can add integrated optic in order to focus the light coming from a light source, in our case, an optical fiber, onto the detection channel. So focusing the light sheet that crosses the detection channel, and then we can perform light sheet fluorescence microscopy, flowing our sample in the sketch cell through the light sheet, and then acquiring the fluorescence with a standard button microscope. The fabrication technique that we use to realize all these elements is called femtosecond laser micromachining. We shine a femtosecond pulse laser into a transparent material, for instance, glass. Because of nonlinear interaction, we can induce material modification only inside the focal volume of the laser. We can induce some different type of modification, for instance, a change of the refractive index. By translating the focal volume inside the glass volume, we can then laser write integrated 3D photonic circuits or waveguides. Another type of modification is called nanograting and allows us to realize three-dimensional geometry. When we expose the modified material to acid attack, we can then selectively etch it out and then realize embedded microchannel with three-dimensional arbitrary geometry or even micro-optics. With this, we have all the elements in order to realize our device with our light sheet fluorescence microscope on chip. Let's start with the scheme for a single cell dual color analysis. We have our two external tubing that connects to a microchannel. The sample then can flow. I will try to use a laser pointer. The sample will flow through the microchannel. We have an external optical fiber that is coupled to an embedded hollow lenses that focus the light into a light sheet of 2 micron thickness. We can then collect the fluorescence from a bottom detection window with our microscope objective. Our device can be mounted on a standard inverted microscope using a high-speed CMOS camera to acquire the fluorescence. The light is coupled from two different laser sources into a single optical fiber that is directly pigtailed to the device, and the flow of the sample and its velocity is precisely controlled with a high-precision pressure pump. Here you can see a picture of our device ready to be mounted on our setup, and you can appreciate that its dimension is less than 1 cent coin. We used our device to acquire three-dimensional reconstruction of single cells. While the cell flow through the light sheet, we can acquire several planes with a resolution approximately similar to half a micron. And as you can see from the images, we have a resolution that is sufficient to recognize the features that are inside the nuclei of the cell. In this picture, in particular, the nuclei are represented in red. Here we have a video of what the system sees while the cell flows through the light sheet. And here you can see a reconstruction that you obtain when you stack together all these planes and you make a section on a perpendicular plane. Even in the reconstructor plane, we can still appreciate the geometry of the nuclei, for instance. We implemented also an automatic acquisition so that the system could work for minutes, even hours, without an operator intervention, and can acquire up to hundreds of cells per hour, taking approximately 0.1 second per cell. Here is a sketch of the system that automatically recognizes the cell and save only the region of interest. Let's now move on the second example. That is the same type of device, but developed for the study of Drosophila embryos. This type of sample is totally different. It has a much bigger dimension, 500 micron by 200, and also it is elliptical in shape. The main challenge in developing a device for this type of sample consists in the scattering induced by the tissue of the sample itself. The two main drawbacks could be the degradation of the light sheet quality while the light sheet crosses the sample, so that we have 1/2 of the sample that is less illuminated, and also the aberration introduced in the detection path by the scattering of the sample itself. The two solutions that we found out to circumvent these problems are to implement a dual-side illumination and also to implement a passive orientation of the sample along its smaller axis in order to reduce the effect of the aberrations. The dual-side illumination has been implemented by duplicating the lens system on both sides of the microchannel and integrating some laser-written waveguides in order to guarantee the precise alignment of the two light sheets. This is an image of the two light sheets that are practically totally overlapped over an area of 500 micron by 400 micron and with a thickness of 12 microns. Concerning the passive sample orientation, we have engineered and optimized the microchannel shaped in order to introduce a control perturbation in the flux and automatically orientate the elliptical sample along its in a horizontal direction, we can say, when it crosses the detection plane. This orientation is totally passive and is induced by the flow of the buffer itself. So here we have a picture of our device when mounted on our experimental setup. You can see the two optical fibers on both sides and a pipette tip that substitutes the external inlet tubing of the previous sketch that I showed you a few slides above, in order to directly inject the sample with a standard laboratory pipette tip. And then we have a syringe pump in order to withdraw our sample. Here we have several examples of different planes of different samples where the nuclei of the cells are marked as small dots. And here we have a video of the sample that crosses the light sheet and it flows towards our direction. So, as a conclusion, I've shown you how we can realize a versatile design to integrate light sheet-first microscopy analysis directly on an optofluidic device, totally integrated, and how this type of design can be tailored to the different characteristics of the sample, thanks to the versatility of the fabrication technique, that is femtosecond laser micromachining. Concerning the first example, that is single cell dual color analysis, I'll show you how we are able to obtain a three-dimensional reconstruction with subnuclear level resolution, and how we can implement an automatic acquisition of hundreds of cells per hour in order to screen out a whole population. Concerning the Drosophila embryo device, I show you how we integrate a dual-side illumination in order to overcome the scattering of the sample, and how we engineer the microchannel in order to orientate as we want the sample during the acquisition. The future perspectives of this type of these devices, for instance, of the device concerning the single cell analysis, is the employment in the study of cancer cell population heterogeneity, and in particular in the investigation of tumor markers related to the three-dimensional organization of proteins inside the nuclei. A further step would be the integration of more advanced microscopy technique on the same type of platform, for instance, lattice structural illumination microscopy, in order to push further the ultimate resolution of the system. So let me thank the project I am involved in, that is called ProChip, my collaborators from CNR and the Politecnico di Milano, and all the members of the consortium. So thanks for your kind attention. If you are still interested, here you can find the link to our social media or even the website.
Thank you, Federico, for a very nice talk. So there are a couple of questions for you. One, what kind of aberrations, specific aberrations were present in your system?
Okay, the type of aberration could be two, if I'm trying to show you, okay, this supplementary slides. We have two types of aberration. One may be introduced by the glass channel itself. So we shape the channel in order to match the numerical aperture of the detection objective in order to reduce this type of aberration, even though we can have some small effects near the edges of the microchannel cross-section. On the other hand, we are imaging through a big volume of water and also a cover zip glass, and this can introduce a spherical aberration. In order to reduce this type of aberration, we used index matching solution in order to raise the refractive index of the buffer up to the level of the surrounding glass media in order to reduce as much as possible our spherical aberrations.
Okay, thank you. There's another question. Which dyes do you use for the fluorescence measurements? What are you studying inside the cells?
Okay, we used for concerning the cells, we used some immunostaining on the alpha tubulin of the membrane, external membrane. That was the green one. I'm moving back to the correct slide, and we marked also some chromatin loci inside the nuclei, still using immunofluorescence, and it was Alexa 488 and Alexa 561. Concerning the Drosophila sample, we used several different types of samples, and the one that I'm showing you in the slides were expressing genetically fluorescent probes inside the nuclei of the cells, and on the muscles, on the muscle cells structure, the video in the bottom. But I don't remember the precise loci code.
There's another question. How does your technique compare to the current state of the art fluidic channels where people use these kind of cell identification?
Okay, we are talking about the microscopy technique or the fabrication technique. Okay, I will answer for both. Okay. Concerning the fabrication technique, it allows to fabricate cells with microchannel with three-dimensional structure spanning from 5 microns to hundreds of microns. So it's really at the edge of the technology. And also in glass medium that is really good for biological application. Concerning the microscopy technique, it allows high image quality and actual good throughput and low photobleaching and high resolution. If we compare to other techniques like cytofluorimetry, we are much slower. But we are not simply detecting the cells. We are actually acquiring a whole three-dimensional reconstruction with high resolution. So we can say that we are almost at the same level at microscopy technique that work on fixed sample as resolution, but we can acquire hundreds of cells continuously without need to change the mounting media or thing like this.
Great. So we have time for one more question. What do you think the challenges are there for your technique to transition it into the clinical settings?
One main challenge could be the typical challenge of microfluidics, that is the connection to the outer world. That is the use of external pumps or connection with tubes that are quite easy to be done in experimental lab, but when we move to clinics, it needs dedicated setup. On the other hand, for instance, if we were able to use much simpler pressure pumps, like in the case of the Drosophila embryo, where we use a simple syringe pump, we can say that it would be quite useful for clinical application, even though we still need to increase the concentration of the sample in order to have a effective continuous delivery and obtain a statistical relevant number of measurements. Of course, when we move towards clinical, obtaining a high number of samples, for instance, of tumoral cells, could be a difficult issue, in particular in the study of tumors and so on. So we probably need stage in order to concentrate the sample to be integrated in the microfluidic circuits, or even an external protocol in order to concentrate it before injecting inside the device.
Okay, so I guess now we are out of time. We have more questions, but I think we are out of time. So once again, thank you, Federico, for a fabulous talk, and we look forward to seeing you again. Thank you.
Thank you.
Okay, so the next talk is by Alexis Scholz. She is a PhD student in the biomedical engineering department at the University of Southern California. And she is doing some really highly impactful diagnostic tool development, especially very useful for low resource settings. So over to you, Alexis.
Great, thank you. Oops, sorry. All right, you all can see my screen?
Yes, I can see your screen.
Great. Hi, everyone. Thank you, Imran, and the conference organizers for having me here today. So today I'm going to be talking about the design of an optical malaria diagnostic system that is optimized for use in low resource settings that we've developed here in the Armani lab. So malaria persists as a highly prevalent and often fatal disease worldwide. According
so maybe
to the
you want to expand your screen so your notes are visible. So maybe you want to expand your screen.
Sorry,
yeah, you're good. Yeah.
Sorry.
Thank you.
All right, where was I? So according to the most recent World Malaria Report, malaria is still endemic in 89 countries worldwide, putting 3.8 billion people at risk of infection. In 2018 alone, there were over there were an estimated 228 million cases that caused over 405,000 deaths. These deaths are particularly tragic when we consider the existence of treatments that are almost 100% effective if they are administered early into disease progression. So now there are a number of reasons for this, but we'll focus on the diagnostic side of things, as obtaining an early and accurate diagnosis is key to treatment efficacy, but can still be very difficult to come by, especially in these low resource settings where malaria is endemic. And this is due in large part to limitations of current diagnostic technologies. So the current gold standard for malaria diagnostics is light microscopy, which is when a technician takes a slide of blood, stains it, and then manually counts the number of malaria parasites present. So although this is an accurate technique that can be used to screen for malaria, it requires expensive equipment and technician training, which severely limits its availability in these low resource settings. So to counter some of these limitations, rapid diagnostic tests have been developed. So these are based on chemical antibody sensing, which allows for point of care use as they can deliver results in about 15 minutes. They're widely available and they're inexpensive. However, they do rely on these chemical reagents that can be unstable in tropical environmental conditions, and they have a lower sensitivity, which can result in failure to detect early stages of the disease. More importantly, a recent World Health Organization report has actually called into question the reliability of some of these tests. So what we're proposing overcomes many of these limitations. So our system relies on a magneto-optical detection of a byproduct of the malaria parasite that's been integrated into a point of care screening device. So our design allows for high throughput testing because each test only takes about a few minutes and has a low cost. The system is designed to be both fully portable and fully automated, so it requires zero training to use. And in addition, we've demonstrated high sensitivity of the system that we believe will allow it to be effective even at the critical early stages of the disease. It will also screen for multiple species of the malaria parasite, and ultimately we believe it will be able to provide information on the parasitemia level of the patient, which is the concentration of the parasite in the patient's blood. So we believe that this system will allow us to pull the accuracy of light microscopy and the accessibility of the rapid diagnostic tests into a single system, filling the gap in the current solution landscape. So before we can talk about exactly how our system works, we have to understand the life cycle of the malaria-causing parasite within the human body. So infected mosquitoes pass on the parasite to people through the saliva in their bite. And the parasite bides its time in the liver, reproducing until it's ready to be released into our bloodstream. And from there, they can enter our red blood cells where they break down our hemoglobin to synthesize their own proteins. However, this process creates an iron-containing byproduct called heme, which is extremely cytotoxic to the parasite. So in order to survive, the parasite converts heme into its non-toxic crystalline form, which is known as hemozoin. The parasite matures and continues to reproduce before eventually bursting out of the red blood cells and continuing on to infect new cells. So the key point in the life cycle for us is the production of this byproduct called hemozoin. So what is hemozoin? Hemozoin is a rod-like crystal that ranges from 300 nanometers to about 1 micrometer in length. And while the crystal morphology varies a bit by species of the specific parasite that we're talking about, all hemozoin exhibits superparamagnetism, which is the property that we will take advantage of. So for example, here's an SEM image of hemozoin on the left, as produced by the most common malaria-causing parasite. And on the right, we have an SEM image of beta-hemotin, which I'll refer to more later in the presentation. But beta-hemotin is the standard synthetic mimic that we can use to just avoid handling actual malaria-infected blood as much as possible and reduce the risk associated with working with these samples. So we're sensing this superparamagnetic nanoparticle that's known as hemozoin that is, again, created when the parasite digests the hemoglobin of our red blood cells. So healthy patients don't have any magnetic substances in their blood, which allows us to leverage the magnetic properties of these hemozoin to screen for malaria based on the presence of hemozoin in our blood. So we do this by taking a blood sample, ideally from a finger prick, but we'll discuss that more in depth later, and we place it in a cuvette. We then shine a light source, which in our case is a 635 nanometer laser, to apply some initial intensity of light to the sample, and then detect the intensity of the light that passes through that sample. And this allows us to use a really simple form of differential optical spectroscopy, where we're detecting this change in intensity as a change in power. So our test begins by taking an initial baseline period, which is currently set to about 30 seconds, where we measure just the power transmitted through the blood sample with no external perturbations. Then we apply a magnetic force, which results in an increase in power transmission in the malaria-infected blood samples, which is shown here by this red line, but not in healthy samples, which are depicted by this black line down here. And the reason for this is actually pretty straightforward. In our blood samples, we have the contents of red and white blood cells. And in infected patients, we also have these magnetic hemazoan particles, which are shown here in blue. Also note here that the laser beam path is shown in yellow just for clarity. Again, we're using a red laser. And when we apply the magnet, these magnetic hemazoan particles get attracted to the magnet and pulled out of the path of the beam, which allows more light to pass through the sample. But in healthy patients, again, we don't have these hemazoan particles, so we see no change in power transmission when we apply the magnet. So the premise of our test is pretty simple, and we previously built a device that utilizes this, implements this test. So we can see the idealized rendering on the right, as well as the actual setup that we built and tested with on the left. So again, the system checks many of the boxes that we believe are necessary for a successful malaria diagnostic that can be used in the field in some of these low resource settings. So for those of you who were at the career panel yesterday, this was the project that Sam McBurney was referencing. And as part of her work with it, she was able to characterize 3 very important sensor characteristics. So the first was measuring the lower limit of detection. So Sam was testing with beta hemotin that was suspended in either polyethylene glycol or whole rabbit blood to more closely mimic a malaria-infected blood sample. And she was able to find that the lower limit of detection for our device is 0.087 micrograms per milliliter. So when we look at the data in general, we can see that as we have decreasing concentrations of beta hemotin, I should say, in our samples, we do see decreasing changes in optical power that is being able to transmit through our sample. And this agrees very nicely with some of the modeling that was done by Dongyu Chen, which is shown here as the shaded regions. So, as far as the differences between testing in PEG versus whole rabbit blood, we can see that the blood cells are causing more noise in our signal, but we can see that our overall results still agree very nicely with our models. Sam was also able to show that the working range of our system includes the clinically relevant range of hemazoans. So that's about less than 1 to 5 micrograms per milliliter. And again, this is very important to show that our sensor can in fact sense what we need it to in order to translate eventually into the clinic. Lastly, Sam was able to show that if we took the same sample and tested it repeatedly, we got reproducible test results, which again, consistency is very important for an eventual diagnostic. So from here, the next step to bringing the system to the world is validating it with an animal study. So for this, we are in contact with collaborators at Emory University's Malaria Host Pathogen Interaction Center, where they already study malaria-infected primates. However, for these animal studies that we have planned, in order to take that step forward, we actually needed to take one step back first. So our initial version of the device that I showed earlier uses a larger sample volume that would only allow us to draw blood from these primates about once a week. And this would have a direct impact on the quality of our studies, as we had planned to monitor hemazoan levels with daily blood draws. So in order to do that, we need to reduce our sample volume size from the initial 500 microliters to the amount of blood that you can obtain from a single finger prick, which is about 200 microliters. So, in the grand scheme of things, that 300 microliters doesn't seem like a lot of liquid, but it actually required us to fully redesign our testing setup. So that's what I've been working on in the past year, in addition to actually making this a fully portable, self-contained system that we could, send to someone and have someone who's completely untrained on it use effectively. So in pursuit of these goals, we've gone through a slew of prototypes. These are the 2 current working prototypes that we have right now. These changes are mostly driven by changes in the magnet we're using. So the first prototype, this is very similar to the initial prototype that Sam used for her testing, uses a permanent neodymium magnet. So think super, super strong fridge magnet. And then a switchable magnet, which is a magnet that's in specially designed housing that contains magnetic shielding, so that when we rotate the magnet, we can effectively turn it on or off. So this switchable magnet allows our prototype to be smaller, significantly decreases the footprint of our device, as well as the power requirements. So it has some big advantages But just because it's more different than our initial prototype, we're currently moving forward and testing with both of them still. So to talk a little bit more in depth about how each of these work, to give you a better idea of what's actually happening, we'll first talk about the permanent magnet prototype. So this is a rendering of the device. We can see the user interface on the top. It's really simple, just some buttons and then a text screen that spits out your results. So as far as actually running a test on here, the user would open up the lid, slide a cuvette down to the bottom. This bottom part, to note, the box is clear just for illustrative purposes here. This bottom part is fully self-contained and closed off. And then to actually run the test, we'd take our initial baseline period, and then our motor will actually physically slide our magnet into place next to the sample in order to apply the magnetic force. So again, this prototype's a little bit bigger. It does require a little bit more power. So we're exploring the use of this switchable magnet. So this box is actually pretty small. You could hold it in your hands super easily. The testing setup here is largely the same, but our magnet is now static. So it's actually positioned behind the cuvette here. And in order to turn it off, turn it on, it's really simple. We just use a servo motor and rotate the magnet within the magnetic shielding to allow the magnetic field to escape the shielding and actually affect our sample. So again, this prototype drastically reduces not only the space requirements, but also the power consumption and the cost of our system. So we're further optimizing the design. So we're currently moving forward, as I mentioned, with validating both these prototypes. And to kind of touch on how we reduce the sample volumes, really simple again. On the left, we have what we were using in the initial prototype. We were using a micro cuvette with the laser beam aligned towards the top of it to avoid scattering off the sides of the cuvette. Now we're using a standard cuvette and just aligning the laser to pass just over the bottom of the cuvette, which conveniently aligns itself to be about 200 microliters in terms of the volume of fluid that's required to get that. So on the right here, we can see initial data that was taken with the neodymium permanent magnet prototype. And this was taken with iron oxide nanoparticles, since that's what we had on hand. Unfortunately, with lab shutdowns related to COVID, we've had some delays in testing our prototypes. But moving forward, we are hoping to validate both prototypes with iron oxide, first with iron oxide nanoparticles, since we have them on hand, across a wide range of concentrations and a wide range of sample volumes to validate that our system does in fact work. And then we'll validate with the synthetic hemozoan mimic beta hemotin that I mentioned earlier. And then hopefully we'll be able to take those next steps to actually getting this technology out in the field, moving forward with an animal study. So I'd like to, acknowledge and thank, of course, my advisor, Dr. Andrea Armani, as well as Sam McBurney and Dongyu Chen for their previous work on this project, as well as everyone in the Armani lab, and of course, the POM organizers for the great conference and the opportunity to speak today. So thank you all for listening, and I'll now take any questions.
Thank you, Alexis. This was a wonderful talk, and we have a lot of questions for this interesting project. First question is, I understand you are using nanoparticles to target malaria. Can this technique be easily translated to diseases other than malaria, such as COVID?
So one thing to note here is we're not actually making the nanoparticles. We're not introducing anything new to the human body. We're leveraging a naturally occurring magnetic nanoparticle, and naturally occurring in the sense that it occurs because of the malaria parasite. So, it could, I guess, potentially be used, or a similar thing might be used to treat other diseases, but you would have to, go through the testing of are the nanoparticles safe to put in the body first, and, all the things that go along with introducing something new to the human body.
Okay, great. And what's the cost of this total system?
So the total cost, I actually have a breakdown here, sorry. Right now, it's at about $1,050 for the neodymium magnet prototype, but with the servo prototype or the switchable magnet prototype, the cost drops by about $100. Obviously, this is like for a single prototype. We think with production, you could decrease the cost of. Obviously, you decrease the cost of anything. So right now, we're looking at about $1,000 for one prototype.
Great. There's another interesting question. Is it possible to get anything else in the blood interfering with your signal depending on patient's condition? Maybe patient is infected with something else. And so will your signal deteriorated or what?
So that's kind of the point of us taking an initial baseline period. So if we go back to the slide that shows the test, this initial baseline period is is meant to normalize our signal to whatever the patient has in their blood. So like any of these red blood cells, white blood cells that are hanging around in the blood, when we actually look at our signal, we're really looking at the change in power between the end power transmission versus that initial power transmission, if that makes sense. So as long as the patient doesn't have any other magnetic substances in their blood, that's the only thing that should change when we apply the magnet.
Is there any particular reason for choosing a 635 nanometer laser? Can anybody use it like a telecom wavelength or some other wavelength?
So this was part of the testing, excuse me, that Sam McBurney did. She found that she got the best results with a 635 nanometer laser. We also wanted to pick something that was readily available and low cost again, right? You can get a really cheap red laser diode because then we're trying to use this in a low resource setting. So all of the things we use, we want to be readily available, easy to replace, as low cost as possible. So it's a combination of, initial testing with different wavelengths and, what's available.
So on the notion of that low cost, do you think that a red LED can replace your laser? Is it possible?
That's something that would be definitely interesting to look at in the future. Since, if we look at the cost breakdown of our device, the most expensive parts are the photodetector and the laser. So it's something that we haven't looked into yet, but definitely something that would be interesting to look into in the future is whether we can use, an even lower cost light source and a lower cost power detector.
Okay. And what do you think, how far you are away from taking your device to actual clinical settings?
First, we obviously have to go through animal studies. So I think we're hoping to get the device to an animal study in the next year or so. Within the year, hopefully. It'll be interesting navigating a cross-country collaboration with COVID. But we're hoping to get it into an animal study, and from there, obviously, you have to go through, stages of clinical studies. So, as far as actually getting it out there, we're still probably looking at years. But hopefully, we'll be moving on to animal studies.
Great. So maybe last question for a few seconds. Do you have a control to compare the results? I mean, a sample without malaria?
Yes, sorry. So I didn't mention that, but we're using essentially, Sam was using either just polyethylene glycol or just whole rabbit's blood, that hadn't been essentially doped with beta hemotin. In my case, since I was testing with iron oxide nanoparticles in water, I've been using just water as a control. But eventually it would just be like a healthy blood sample versus a malaria infected blood sample.
So great, Alexis, and we look forward to seeing your device to actually into clinical settings. Thank you very much for your time and talk. Good luck.
Thanks.
Okay, so now we are moving to the last talk of the session, and it will be given by Siu-Ju Bae. She is a PhD student in electrical and electronics engineering department at RMIT University, Australia. And she's doing some outstanding work on using frequency combs-based biosensors. So it's over to you, Siu-Ju.
Yes, thanks. I'm looking to share my screen. Just give me a second. Can you see my screen right now?
Yes, we can see your screen.
Okay, right. Hi, everyone. My name is Sue, and I'm a PhD student here at Integrated Photonics Application Center at RMIT University, Australia. So today I'll be discussing the advantages of using optical frequency cone-based silicon photonic biosensor for the blood biomarker analysis, specifically in the context of heart attack from a biomedical scientist point of view. So I want to start my talk with a story. Nancy is a 58-year-old woman who enjoys regular exercise. She eats healthily and has no known family history of any genetic disease. But one day she was rushed to the hospital. She had the symptoms of dizziness, sweating, and shortness of breath. So the doctors performed all sorts of tests on her, but they came back normal. They suspected that she was experiencing heartburn and possibly early menopause, but for the next week or so, her condition went from bad to worse. She continued to take the prescription that was given to her, but she was actually suffering from something called the silent heart attack. And this was only made known to her when she was admitted to the hospital a week later with her blood test showing signs of elevated troponin. Now, in healthy individuals, troponin levels are very low. When someone suffers from heart attack, the troponin is released from the damaged heart muscles and into the bloodstream. So nearly 1 in 3 patients with heart attack had other diagnoses at first medical contact, and this is especially more common in women compared to men. So it's very important for blood testing to be done as quick as possible, because the longer a heart attack is left undiagnosed and untreated, the more the heart muscle can be permanently damaged. So with the conventional blood testing, if one were to consider the entire process, starting from taking the blood to analyzing it and delivering the result to the hand of a clinician, it does take a long time. And Nancy might have not been so lucky if there was any delay between this process. So to streamline this, researchers have turned their attention to a highly compact system known as lab on chip. The aim of a lab on chip is to really shrink the entire lab function into a chip using nanotechnology, where the analysis can be carried out in a fraction of time and in a way smaller scale. This also led to the development of an alternative testing known as point of care. Point of care is a portable device that allows for really quick diagnostic testing, but retains the sensitivity and the accuracy that rivals the conventional lab testing. So this is very useful when access to healthcare resources is limited. There are already troponin point of care out there in the market, but they're not widely used because they're not really that reliable in terms of accuracy. What makes a point of care itself is the biosensor. So today we heard a lot of biosensor from many incredible researchers. So what I really want to focus on is the Mach Zehnder interferometer biosensor. So a Mach Zehnder typically consists of 1 splitter, 1 combiner, and 2 waveguides. So when the waveguide is split into 2 arms, one of the arms measures the refractive index change caused by the interaction of the bioconjugate. The other one serves as a reference that cancels out any non-specific interaction. The sensing occurs within the evanescent field, and this is how the output signal typically looks like. So whenever the interaction occurs within the sensing field, you will see a change in phase shift due to the change in refractive index. And this is proportionate to the concentration of a measured target. But there is one drawback to this. An interferometer needs to be biased for maximum sensitivity at the quadrature point. So bias drift exists, which may be due to temperature or other factors, or very, very large signals can result to this bias to be shifted away from the point. So the further away it is, the less sensitive the measurement becomes. And when it hits the peak or the null of the curve, the sensitivity completely vanishes. And this becomes very difficult to distinguish between genuine biointeraction or if it's just a mere fluctuation of the light being sent to the sensor. And this becomes a major issue when dealing with complex samples such as blood, because blood contains not just a biomarker of interest, but many other foreign particles that interferes with the reading of the sensor. Here is our silicon photonic biosensor platform. You can see this is how it looks like in the lab. The silicon chip itself, the layout is seen down here, is fabricated with an array of asymmetrical Mach Zehnder interferometer sensor. When I say asymmetrical, it just means that both the arms are not the same length. The sensor arm is actually way longer than the reference arm, and it's coiled around to minimize the space it requires. So the longer the arm is, the more sensitive it is. Each of the sensor here can detect down to 10 to the power -7 refractive index units, which correspond to picogram per mil measurements of the protein. So when the platform also has an integrated microfluidic device, I don't know if you can see it, it's kind of transparent. That allows for automation and also multiplexing. So when we design the biosensor, we have to ensure that it can be developed into the point of care device, and it has to, based on the international heart attack guidelines, for it to be usable in clinical setting. I'm just going to quickly go through this. When we tested the biosensor systematically, we started from the bulk refractive index change using hydrochloric acid. We then tested whether the sensor is, when we immobilize the troponin antibody onto the surface, we want to see if the antibody are binding to the surface. We also look for specificity. What this means that we want to make sure that only troponin molecules are binding to the antibodies, and we use other common protein that are found in blood to test this out. Finally, we also check for the sensitivity and the limit of detection using different concentration of troponin. So what we found out that is that the biosensor is able to measure cardiac troponin, but the limit of detection did not reach 10 picogram per mil, which was the benchmark for a point-of-care device. It also has a couple of shortcomings from the photonic side of things. So number one, it's not that easy to use. One of the criteria of point-of-care is really the practicality as well. So currently the sensor needs to be biased and calibrated at the quadrature point, and this step needs to be repeated every time a new measurement is started. The current readout method is also quite unstable because remember what I talked about the shift in the quadrature point, it's happening quite frequently. That's because it's very vulnerable to external factors such as temperature fluctuation. You can see here in this graph, the temperature was shifting even though it's by a very small amount. And every time I bump into the table when the system running, I do see a huge change in refractive index. The last limitation was the signal to noise ratio. We want to be able to achieve high signal and low noise because at higher power, the more sensitive the sensor is, but this also causes higher noise generation. We did a comparison with hydrochloric acid and troponin. So with a simple solution like hydrochloric acid, we can see clear change in bulk refractive index. We see very low signal to noise ratio here. But with complex solution like troponin, the noise to signal ratio become a bit hard to distinguish, especially at lower troponin concentration. If you see it up here, this is 0.5 microgram per mil troponin, and we compared it to 0.01 microgram per mil. So the baseline for the 0.5, when we introduce it to the sensor surface, we found that it doesn't return to the original baseline. That shows that it's actually, the troponin is actually binding to our antibody. But with 0.01 microgram per mil, we could barely distinguish both of the baseline when the troponin was flowed to the sensor surface. So to overcome this limitation, we chose to use optical frequency comb technology to improve the signal processing method. So to my understanding, a frequency comb is a tool for measuring different frequency of light. It's like a ruler for light frequency, but in optical hertz. So if you zoom into this optical spectrum here, you'll see millions of little teeth, which are the optical pulses. There will be a series of talk on about frequency comb after this, so I'll just leave the in-depth explanation to the experts. So the method we propose here is to use 3 laser lines from a single electro-optic frequency comb. They are split into 3 channels using a demultiplexer, and the detection is measured through 3 photodetectors and recorded over time. So the comb spacing is adjusted to sample the spectral response at 120-degree interval. So whenever we see a change in refractive index, we see a same shift in phase occurring. But unlike the default setup that I was using before, the measurements are taken at this interval. And all these 3 measurements are then combined as a vector sum, and the angle of the resulting phasor is the phase we want to extract. So this way, we see a continuous and linear phase readout, and this is independent of any bias drift. We look at 3 main parameters when we set up the experiment. We want to see how this setup responds to very large signals. We want to see if it's robust, and if it does reject any common mode signals. So we test out the responsivity of large signal using sodium chloride solution. Currently, I don't have any result on troponin because lab access were very limited during the lockdown here in Australia last year. So the troponin stuff are still work in progress. When the sodium chloride solution will flow through the sensor surface, we did see a continuous and linear phase readout. And then we compared both of this method and found that the extracted sensitivity and the noise were quite similar in value, but the signal to noise ratio were much lower for the comb. And this was to be expected because the inaccuracy of reading only comes from small signals at very low analyte concentration. Also keep in mind that sodium chloride is a much simpler solution compared to troponin. So this system does eliminate the very complicated manual phase correction step that I mentioned before. We then look at how strongly the extracted phase signal is influenced by transmission power changes that are not caused by the operation of the sensor. For example, of factors that could influence this are misalignment or vibration to the fiber coupling of the photonic chip, or fluctuations of the laser power. So the working principle of the frequency comb is shown in the diagram on the left here. So the comb method combines 3 measured power value as a vector sum. And if you see here, in blue, the S here is the phase angle resulting phasor, which is the phase value we want to extract. So if there's any change in signal amplitude, we will see all 3 channels experiencing the same change in amplitude as well. But on the other hand, for the default single wavelength method, we found out that it's very reliant on the projection of the phasor S onto the real axis, which is shown in the red arrow. So any changes in amplitude become indistinguishable from changes in phase. And therefore, that's why the single wavelength phase method is very vulnerable to common mode noise and instability. So when we run the experiment, we changed the input of power stepwise. So with the default single wavelength method, we see that in the first graph on the E here, we find out that it changes linearly with the input of the power, and that was to be expected, while the extracted phase with the comb sampling method remains almost flat. And then when we introduce very large changes of the input power, we see that the single wavelength method immediately loses signal at about -5 dB, while the extracted phase for the comb sampling method remains quite constant until the -50 dB. And we conclude that the comb extraction method is actually suppressing the common mode noise by a factor of about 120 compared to the single default wavelength phase extraction method. So just to conclude, the optical comb processing method can be applied to any pre-existing interferometer and does not require any physical modification to the sensor design. And this can be applied to just about any blood biomarker-based disease, such as ovarian cancer and so forth, not just heart attack. There are a lot of work needs to be done to ensure our photonic biosensor can be transformed into an acceptable point of care. We're looking at surface marginalization and deeper understanding of the troponin molecule itself. Finally, I'd like to acknowledge my group impact at RMIT Australia. So I welcome any question. Just want to point out that I'm a biomedical scientist who works in a very multidisciplinary team. I might not be able to give a very technical question, might not be able to answer a very technical question about the optical frequency comb, but I'll give my best shot. Thank you for listening.
Thank you, Sue, for such a nice talk. There are a few questions for you. So I'll start with this. Is there any dependence of sensitivity or other parameters of your sensor on the Vpi voltage?
Sorry, can you say that again, the last bit?
So is there any dependence of Vpi, the sensor where you have a characteristic Vpi voltage, where the sensor response becomes null? Is there any dependence upon that voltage?
Not at the moment with the optical comb frequency method, but it does have it with the single wavelength phase extraction method.
Okay. What is the working range of troponin detection? How does this compare to clinical levels?
So the working range we have right now is between 10 to 500 nanogram per mil, as in the slide here, and that's not good enough. For the clinical level, the limit of detection, we want it to be about less than 10 picogram per mil. The range, it has to cover from 10 picogram or even lower up to like very high value, like 500 nanogram per mil, because when somebody suffers from heart attack, it does goes up to about 100 to 200 nanogram per mil.
Okay. There is another question. How did you measure noise on your frequency combed biosensor system?
How do I measure the noise?
Yeah.
So there was a very complicated what would I say, calculation that were used, but it's actually done by another student, where he has written up a whole program for it, and we will just transfer it into this program. It will be able to calculate it directly for us. So I don't know how to explain that in a better terms.
There is another question. Why didn't you use reference asymmetric Mach-Zehnder to compress signal to noise ratio, thermal and mechanical fluctuations?
Sorry, it lagged there for me. So why do I not use asymmetrical Mach-Zehnder interferometer to?
Why not you apply a reference arm, a typical technique people do.
There is a reference arm. That we actually do have a reference arm here. If I show you this. So there is a reference arm. It's just shorter than the sensing arm. It is still a typical Mach-Zehnder interferometer.
Okay. Okay, I think that's all for this session. I'm grateful to all of the attendees who attend this session. And do not go away. We have another session in about 50 minutes at 5:35 Eastern Time on the frequency combs. So see you then. Bye-bye.
Hello, everybody. My name is Alessia Pasquazzi from the EPIC Lab at the University of Sussex in Brighton, UK. So for the people that just connected now, this is COM, and I'm very excited to chair the Frequency COM session. Before going into detail, I want to add also my personal thanks to Orad and Andrea, who have organized this conference. During these months behind the scene, I have witnessed to the passion and dedication that they have put in these amazing events. So thank you also from my side. The community really needs people like you, capable not only of inspiring the others with the science, but also able to bring people together and turn on the spotlight on the talent and the diversity of our amazing photonic community. Talking about science, we are concluding this conference today with a set of exciting talks about optical frequency combs, and we will open out with our invited speaker. I'm very happy to have today Miriam Vitiello, who has joined us with a perspective on quantum cascaded optical frequency comb at terahertz frequencies. Dr. Vitiello has received her master and PhD degrees in physics from the University of Bari. She has worked on many high-level institutions in Italy and Europe, like the CNR INFM in Bari, Scuola Normale Superiore di Pisa, Technical University of Delft, the University of Munich, and the University of Paris 7. Dr. Vitiello coordinates now the activities of Terahertz Photonics Center at CNR NanoNest, and she is member of the scientific committee of more than 40 international conferences in the field of photonic devices. She is the recipient of many prizes, the Guido Dorso Research Prize in 2016, the SPA in 2015 Early Career Award, the Sergio Panizza Award of the Italian Physical Society. Before leaving the spotlight to Miriam, please remember to put your question in the chat for a chance to have them discussed with her live. I leave now you with Dr. Miriam Vitiello with Terahertz Quantum Cascade Laser Frequency Combs. Thank you, Miriam.
Thank you, Alessia. I try now to share my screen.
Yes, please take your time.
Yeah. Can you see the screen?
Yes, we see it well. Wait for the full screen.
Yeah, okay, it should be there.
Miriam, we still see the presenter mode.
Okay, I've put them in the full screen, so you should see the full screen now.
Let's see, we still see in this moment, yes, now we see the full screen.
Okay, perfect. So thank you very much, Alessia, for the introduction, and also let me thank the organizers for inviting me to these photonic online events that in this pandemic time, it's really appreciated to have a chance to present the results. So in this talk today, I will try to give an overview of the present state of the art in the field of Terahertz quantum cascade laser frequency comb, and also I will detail a little bit more about our recent achievement in the field that we have done in my group in collaboration with some other institution in Italy and also abroad. So just a few words about the concept of optical frequency comb synthesizers. So the optical frequency comb are nowadays considered one of the most important photonic tools of the third millennium because they have a huge perspective in a plethora of application fields. So the definition of a frequency comb, it's a sequence of optical modes which are spaced in frequency, evenly spaced in frequency. It's a coherent state of emission that can give rise to broadband emission in many frequency range that can be described by a total complex electric field, which is given by the sum of the amplitude of each individual comb tooth, and also by a factor which is accounting for the phase of each individual optical comb mode, which is averaged together in an exponential function. The frequency comb is usually defined by keeping in consideration two very important parameters, which are extremely important for the optical frequency comb, that is the mode spacing, also called the repetition rate of the comb, and also the carrier offset together with the phase, which is of course the parameter appealing for defining and also creating a difference between broadband emission and what is called emission from a frequency comb. Traditionally, the way to generate an optical frequency comb synthesizer is from a passively modulated laser, and there are a plethora of examples, especially in the visible and in near infrared, like for example what has been done with titanium sapphire lasers, or also with fiber laser. There are many fiber laser comb, especially in the visible and in the near infrared. If we would like to have an example of what it is a pulsed frequency comb, like a frequency comb which is conventionally generated from a near infrared or a visible laser, it is just in the frequency domain. It can be seen like a sequence of optical modes, which, as I said before, are evenly spaced. But if we look to the time domain, the intensity of these optical modes can be reproduced in this way. So you can have a sequence of peaks which are iterated in time. And if we look to the intensity of the peak, it is the same at a specific position at a specific time. And then on the low frequency, on the low time side and on the high time side, it is giving a kind of decay like that. And basically, in order to have an optical frequency comb, a pulsed optical frequency comb, you should have that a specific instantaneous intensity. The amplitude of this mode should have this kind of composition, which translated in the phase, it's given by the fact that at the center of this peak, you have a linear trend between the phase of all optical modes, which share exactly an identical phase, which in this graph is equal to 0. And when you move farther from the peak that you see here, you see that this kind of linear behavior still remain linear, but you have a little bit of spread of these phases, which is from the top to the sides, following this kind of time delay. But very recently, the concept of optical frequency comb synthesizer has been also extended to the infrared and also to many miniaturization configuration, like, for example, microresonator ring, or, for example, passively mode locker interband cascade laser. And a few years ago, this was also in the group of Jerome Feist at ATH, the first demonstration of a quantum cascade laser's frequency comb at mid-infrared frequency. The concept of a generation of a quantum cascade laser frequency comb is a little bit different with respect to what I have presented just a few minutes ago, because it is a continuous emission from this laser. And basically the concept behind the operation of a quantum cascade laser comb is four-wave mixing, which is practically induced by a strong order nonlinearity inside the waveguide of this material system. This means that this kind of laser are optical frequency comb, but they do not emit short pulses, so it's not a mode-locked laser. Basically, the principle is degenerate and non-degenerate for wave mixing, but I will come back to this concept a little bit later when I will going into the details of terahertz frequency comb. So why there is a huge interest today to push forward the concept of optical frequency comb synthesizer into a miniaturized configuration also in the terahertz regime? Because the terahertz frequency range, which is conventionally located in between the range of interest of microelectronic and photonic devices, has an amazing potential for many application fields, and specifically also for spectroscopy, for metrology, and for imaging application. So the need of a broadband source, which is coherent, miniaturized, specifically electrically pumped, meaning that you can create a more compact and also do not have a bulky configuration to generate an optical frequency comb. It's very important. Also, the quantum cascade lasers conventionally has very high power, wide tunability, and also very limited line width, which are very important for spectroscopic application. And this is the reason for what the terahertz quantum cascade lasers emerged like one of the most important photonic tools to try to see if we can use this kind of tool to generate an optical frequency comb, to employ this kind of devices for metrological and spectroscopical application, which require accuracy and also huge precision. And just to give an idea to people which are not confident with the concept of a quantum cascade laser, the quantum cascade laser is an inter-subband laser, meaning that you have a stimulated emission from states which are localized in one band, which is the conduction band. And this is a table which is summarizing the actual state-of-the-art performances of quantum cascade lasers operating at terahertz frequency. So you can have a frequency coverage which can go between 1.2 up to 5.6 terahertz. You can reach maximal optical power in pulsed mode of the order of 2 watts. And they are lasers characterized by very small intrinsic line width of the order of 90 Hz. This means that they have a very high spectral purity. They are frequency tunable, almost around 10% of the central frequency. The actual record of operating temperature is 250 K. This is the results of a few months ago. It has been reported at MIT in the group of Xingu. And in continuous wave, they operate up to a maximum temperature of 143 K. In terms of gain bandwidth, they can cover up to an octave spanning, and with heterogeneous design, you can reach up to almost 2 terahertz of frequency coverage in the field. Another approach to generate terahertz emission from a quantum cascade lasers, it's characterized by the so-called difference frequency generation. This is an approach which combines 2 mid-infrared quantum cascade lasers embedded together, and thanks to the four-wave mixing between the 2 mid-IR, you can generate a terahertz emission up to room temperature. So these lasers operate very well at room temperature, of course with the reduced optical power, since the inherent process behind the emission of terahertz radiation is not a direct process like before, but is different frequency generation and mixing between the 2 mid-IR lasers, but with amazing performances also in terms of spectral coverage. So basically, the idea, you have a quantum cascade laser emitting a terahertz frequency, so you can use the so huge intrinsic nonlinearity in the active medium to generate through four-wave mixing the optical frequency comb synthesizer. However, since the four-wave mixing generates this evenly spaced optical mode that needs then to be injection locked inside the cavity, the concept is that this locking mechanism has an infinitive locking range, but the dispersion in the cavity needs to be low enough in order to have all cavity modes within this locking range. But this is a huge problem at terahertz frequency, since the 3-5 materials which are conventionally employed to fabricate this terahertz QCl, like gallium arsenide, aluminium gallium arsenide, are extremely dispersive at terahertz frequency, and this means that injection locking cannot occur when four-wave mixing is very far from resonance. The first report of terahertz quantum cascade laser frequency comb dates 2014, and it is a work pioneered in the group of Qingwu by David Burkhoff, which is also one of the speakers today. And the idea, the nice idea that they have developed is to try to compensate this huge dispersion at terahertz frequency by tapering and chirping the waveguides in order that the frequency is chirped and the amplitude is tapered. And in this way, they demonstrated the first terahertz quantum cascade laser frequency comb, which was operating as an optical frequency comb synthesizer only in some small portion of the operational regime of the laser, very close to the peak optical power of the laser in these cases. The same year, there was also one report in the group of Jerome Feist by also Giacomo Scalari and co-workers, in which they have demonstrated an octave spanning semiconductor laser, and in this case, the idea is the waveguide is a standard waveguide, but they combine it together more than one active region, creating an heterogeneous stack in order to make broader and broader the emission bandwidth of this kind of laser. With a dynamic range, in the first report, it was of the order of 1.4, and in a report a little bit a few years later, they reached a dynamic range of 2. Again, the quantum cascade laser frequency comb was operating as a frequency comb only in a small portion of the operational range of the laser, which in this case is of the order of roughly 50 milliamp. And also the idea that they have developed, also in collaboration with the group of Charlie Interreiner in Vienna, is to put some side absorbers on the top of the cavity of the QCl in order to cut the lateral modes and to make more stable and also very well equally spaced the optical modes that have been emitted by the lasers. Also, a few years later, this is a work more recent, the idea of generation of an optical frequency comb synthesizer for quantum cascade lasers has been also pioneered with the use of the difference frequency generation at room temperature. This is a work done in the group of Maniger Azzeghi at Northwestern University, and it is the first demonstration of a terahertz semiconductor frequency comb operating at room temperature. The drawback of this approach is, of course, related to the poor optical bandwidth, because they can practically provide the frequency coverage only in a very small portion of the spectral bandwidth, and also the delivered optical power is of the order of a few nanowatt, but the great advantage is that this device operates at room temperature. So the interplay between the four-wave mixing and the group velocity dispersion in the cavity has a very important role in determining the degradation mechanism behind the operation of this frequency comb. Therefore, the medium engineering is very important in order to create a flat top gain on the top of the desired operational bias of the laser, meaning that you should work very well with the nature of the gain median in order to avoid that the dispersion entangle the dynamics of comb operation and other biases. So what is the state of the art presently? So frequency comb operation, it's usually achieved in an operational range which is less than 25% of the total range of the laser when you deal with heterogeneous QCl, and with homogeneous QCl you can reach 29-30% 30% of the operational range of the laser with a stable frequency comb regime. But many approaches have been pioneered in the recent year in order to try to extend the operation of the quantum cascade laser at terahertz frequency as a frequency comb also in a much broader frequency window. And also in my group, we have worked a lot in the last year to try to see what are the better approach to try to increase more and more the operational range of the laser. And I'm going now to present a few results that we have recently achieved. So what have been done so far in the literature, starting from the first demonstration that I have just cited a few seconds ago, the first work of David Burkhoff. As I said, the operational range was 29% of the operational range of the laser, in which the device was operating as a stable comb. And also a few years later, the same group have also reported the demonstration of a terahertz frequency comb synthesizer operating as a comb over the entire dynamic range of the laser. The approach here is a kind of active approach that creates a kind of gap between two semiconductor sessions. They have applied a DC bias to one session in order to modulate the other part of the laser cavity and to push the operation of the device as a stable frequency comb over the whole range. Again, here there is the drawback that the power emission is not so high, so the comb was emitting a maximum peak power of a few microwatt, and the spectral coverage was of the order of 400 gigahertz. Also, a different other kind of approaches has been pioneered at ATH and also another group. This is a recent work of 2019 in which there was a demonstration this time of a homogeneous frequency comb that was working quite well, also very good power output. But again, the frequency coverage was good, but roughly there was a bandwidth, as you can see in this graph, going above 1 terahertz, roughly 1.5 terahertz, but the laser was operating as a comb only about 29-30% of the operational range of the laser. A few months ago, we have reported the first demonstration of an optical frequency comb synthesizer still employing an homogeneous schema, which is totally passive without any kind of external component that was modulating the emission of the laser, that was operating as an optical frequency comb synthesizer over the entire dynamic range of the laser. As you can see from the graph, the spectral coverage was of the order of 640 gigahertz. And the good thing is that this device was also providing a very good power output. Practically, there was a maximum peak power of 8 milliwatts. So the laser was delivering during comb operation 8 milliwatt, meaning that with the spacing of the optical modes over the bandwidth, we have a set of 200 microwatt of optical power per single comb tooth, which is a power level that has been unreached so far in an terahertz frequency comb synthesizer. And also, we have worked a lot extensively in the last year also on heterogeneous frequency comb synthesizer with two targets. The first target was to try to increase the dynamic range in which the device was emitting. And one of the first results that we have achieved a couple of years ago was a terahertz frequency comb synthesizer employing an heterogeneous scheme in which the dynamic range was a factor of 3.2. The definition of dynamic range is practically the ratio between the maximum current density of the laser divided by the threshold current density of the laser. And this has been achieved by multi-stacking together 3 active regions that were sharing the same threshold current density, but they were slightly detuned in frequency of a factor of 500 gigahertz. And this is the intermode bit note map of the laser. So it is practically the bit note frequency between the emission, the individual comb emission of the laser plotted as a function of the current, and the intermode bit note line width. It's just a genuine way to see if the device is operating as a frequency comb. It's not a way from which you can retrieve the phase of the optical mode, but is a genuine indication of a comb operation of the devices. And as you can see from the graph, the device was operating as a frequency comb in a range of current roughly of the order of 130 milliamp, but then the operational range of the device is fully dominated by dispersion. So the devices, its mode are unlocked. There is the dispersion that is practically putting the laser and driving the laser in a regime in which the modes are no more stabilized in phase. And with these lasers, we reached this spectral coverage of the order of 1.05 terahertz, and the COM regime was characterized by an optical power output of the order of 0.75 milliwatt with 55 equidistant optical mode. And we have also characterized the tuning of the intermode bit note in terms of temperature and in terms of current, reporting tuning coefficient that are quite appealing for application in spectroscopy, because we get with current a tuning coefficient of the order of 5 megahertz over milliamp in the first portion of the operational range of the laser, and in the second portion it is slightly less, it's of the order of 2.1 megahertz over milliamp, and a thermal tuning of the order of 90 megahertz in total in continuous wave during the frequency comb operation of our devices. Then we also try to push forward this operational behavior of this laser, trying to reach a condition in which we can increase even more the operational range in which the device was operating as a stable comb. And to do that, we demonstrated a configuration which is based on the presence of a movable mirror, which is closely coupled with the cavity, in particular with the back facet of the laser, building up the so-called Gir-Tournois interferometer. So the idea is that we create a kind of external cavity in which the Gir-Tournois interferometer operates in reflection, with the front mirror characterized by very low reflectivity and with the back mirror which is conversely perfectly reflective. And so the idea is that moving this metal mirror, you can practically tune the group delay dispersion in the cavity of the quantum cascade lasers, and you can practically adjust the phase of the optical mode to try to put them in phase. And the two graphs below show some simulation of the group delay dispersion, the total group delay dispersion as a function of the distance between the back facet of the UCL and this gold mirror, which is we place it on the back inside the cryostat. And you can see that there is a particular condition that we will see later is also periodically repeated, in which the total GDD can be compensated. So we can reach a condition in which we can put down the total group delay dispersion. And when you move far by this mirror, conversely, you reach a condition in group, you cannot compensate the group delay dispersion. What we have observed is that by fixing a current and by moving this mirror, we can iterate this condition of periodic compensation of the group delay dispersion with a certain periodicity. So the Gir-Tournois interferometer can tune between a condition that is called on resonance from a condition in which it is called off resonance. And collecting again the intermode bit note frequency, what we have observed is that we can observe a periodical stringing of the intermode bit note line width, meaning that we can increase the operational condition in which the device is operating as an optical frequency comb when the GTI is operating on resonant, and vice versa, when we put it out of resonance, we cannot achieve compensation, and again, the regime is fully dominated by dispersion. Of course, this kind of approach cannot allow to compensate the dispersion over a broad portion of the operational regime of the laser, but what we have achieved is only 35% wider range with respect to what I have presented before, which is the bare laser. But still there is a not negligible effect, which is also reproduced in the analysis of the intermode bit note line width of this bit note that we have collected. Indeed, if you see the comparison between the black trace, which is the bare laser, and the red trace, which is the laser coupled with the mirror under the so-called on-resonant condition of the GTI, you can see that in the region called number 2, the comparison between intermode bit note line width show that we can reduce significantly by more than 4 orders of magnitudes the intermode bit note line width, forcing the device with this mirror to operate as an optical frequency comb synthesizer in a regime in which it cannot spontaneously behave as an optical frequency comb synthesizer. And these are the comparison between the emission spectra in the condition in which the device is operating as a bare laser, which are the red spectra, the blue spectra, and in the condition in which there is the black mirror, the gold mirror on the back, and so the Gir-Tournois interferometer is acting in its own resonant condition. As you can see, although you cannot unveil a very visible change in the spectra because the equally spaced optical mode are still there, you can see in the intermode bit note line a significant difference because you have with the GTI a presence of a huge in terms of dBm intermode bit note line width, which is also very narrow, and conversely, you see a regime fully dominated by dispersion in the case of the bare laser. More recently, we have tried to push forward this concept, employing a different kind of architecture. So we have fabricated a tunable grating-gated graphene on polyimide modulator, and we have discovered very nicely that this modulator is not only working very well like an amplitude modulator, but is also working very well like a dispersion compensator for a quantum cascade laser frequency comp. The idea is very simple. So you have a waveguide which is created with a silicon substrate and a very thin layer of polyimide which act as a dielectric spacer, and the thickness of this polyimide layer has been matched with the lambda/4 mode of the waveguide, so the central frequency that we wanted to use to engineer this modulator. And then we placed it on top single layer graphene, so large area CVD graphene that was acting like a capacitor over the polyimide layer. And then we have created a metal grid on the top, and the pitch of this metal grid has been selected and changed and also tuned in order to match the central frequency optical mode. So practically the idea is that this metal grating can couple with the quarter waveguide mode, define of course the resonance of our modulator, and also can act like a counter electrode for the single layer graphene capacitor in order to electrically tune the property of the graphene. This modulator we discovered that work very well in terms of amplitude modulator, capable to provide the modulation of the order of 90%, also quite well in terms of speed, because the speed is of the order of microsecond, a little bit less than microsecond. The spectral coverage that we have demonstrated so far, it's between 1.9 and 3 terahertz, but of course it can be changed and also increased simply acting on the pitch of this metal grating. And it is a component which is miniaturized, is passive, and can be embedded on chip with the quantum cascade laser inside the cryo. And indeed what we have done, we have coupled on chip this graphene on polyimide modulator to simultaneously modulate in amplitude QCL and also to compensate the dispersion. And what we have observed very nicely, that with respect to what I've shown before, it provides a completely reshaping of the intermode bitnode line, with also defining a range independently from the pitch in which the device show a very stable operation.
It appears that we are having a few technical problems at the moment. So while we are waiting that Miriam is connecting back, please, I can invite you to keep writing your question to the question and answers. And I hope that we will have the possibility to ask them to Miriam as soon as possible.
Can you hear me? Can you hear me?
Yes, 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 we do hear you. Miriam, we don't see you anymore.
Can you hear me?
Yes, we do.
I'm so sorry. I think there is an issue with the connection.
Yeah, this is it may happen.
So sorry. I will try to. I think I'm not allowed anymore to share my screen.
It's something that
it's written host disable attendee screen sharing.
Yes, yes. Yes. So, Miriam, while we wait for this to fix, shall we? Okay, so we could. Okay, no. So you're back in full screen with everything. Thank you, please.
Okay. So sorry. I will try to go a little bit fast in order to keep the time as I can.
Yes.
So sorry. So very quickly, together with that, we have also developed very recently also another approach in which we try to place the solution processed graphene ink directly in contact with the back facet of the QCL, still with the same idea to try to increase the operational range in which the device was operating as a stable comp. And as you can hear, with this kind of approach, we not only achieved a huge increase in the optical power output of the laser itself, a very good spectral shaping of the spectra by using graphene. We reached an emission with 80 milliwatt with 90 optical modes, but very nicely, the very good results that we achieved, I think that is not going, I don't know what is happening. Can you see the screen? But okay, so the idea is that this component that we placed on the back facet is working as a printable saturable absorber. So what we have demonstrated is that by creating this solution processed ink placed on top, it can behave very well like a saturable absorber at terahertz frequency, showing up to 80% transparency modulation. And the very good thing that we have achieved when we placed it in contact with the back facet of the QCL is that we finally reach a spectral coverage, very huge, and simultaneously emission as an optical frequency comp synthesizer over more than 50% of the laser operational regime. So the laser was behaving as a stable comp also in the most interesting region in which the quantum cascade laser operates, so close to the peak optical power that is almost of the order of 8 milliwatt. And very nicely, the intermode with not line width in these cases was very sharp. So we reached the line width less than 1 kilohertz of the order of 600 hertz. And very nicely, this kind of behavior, very differently with what I have showed before, is not due to dispersion compensation, but is due just to the fact that the device is operating like a saturable absorber. And in order to prove that, we made some kind of experiment simply by changing the position of the ink and moving the distance between the zinc and the back facet of the QCL. And what we have observed is that very differently from the previous report, this is not inducing any kind of change. So it is not a matter of GDD compensation. Conversely, if we do the same experiment placing simply silicon, which is a substrate on which the graphene ink is deposited, we do not see any kind of difference in the intermode with not line width of the laser. And so the explanation of that is that practically, since the operation of an optical frequency comp synthesizer is simultaneously due to frequency modulation and also amplitude modulation, here what we have is that the frequency comp, four-wave mixing in a frequency comp can be generated either by fast saturable gain or loss in a semiconductor laser. Saturable gain usually leads to a frequently modulated output, while vice versa, saturable losses lead to an amplitude modulated output. Here what we have is that we have a saturable absorber, which is especially separated from the gain media. And so practically the injection of the cavity over the saturable absorber create the same kind of mechanism that is induced when you mediate together the saturable absorption and the saturable gain. Or another way to see the problem is that the graphene is also behaving like a Fresnel reflector, and this Fresnel reflector practically combine with the saturable gain of the active media and simultaneously induce a frequency modulated output, while at the same time, at the same moment, the saturable absorption contributes to an amplitude modulation output. And we have performed also a theoretical analysis by means of Maxwell block equation. I do not have time to give into the details, but this kind of theoretical analysis demonstrates very well that there is this shrinking of the intermode binode line width in this kind of configuration by using this graphene ink. Then very, very quickly, I also would like to give an idea of the different kind of characterization technique, more precise, that you can adopt in order to demonstrate that your device is behaving like a real comb. So one of the most used and employed technique that has been developed again by David Burkhoff and Chingu is the so-called swift spectroscopy, which is a procedure from what you can really retrieve and reconstruct the optical phase of the optical mode by moving the mirror of an interferometer, by making a kind of sum of the reconstruction of the phase in different interval that you can have when you move this mirror. And another kind of approach that we have pioneered in Italy in a collaboration between my group and the group of Paolo De Natale at the National Institute of Optics is by means of this kind of phase technique that we call it Fourier transform analysis of the comb emission that we have adopted to demonstrate the first fully stabilized terrestrial frequency comb synthesizer. The idea is fully based on a multi-heterodyne detection scheme in which practically you can control simultaneously with this technique the two parameters of the comb, so the repetition rate and the offset. And what you did, you create a mixing between a free-running optical frequency comb synthesizer, which is generated by a nonlinear waveguide, with the frequency comb synthesizer emitted by the QCL. And the frequency mixing results in a down-converted radio frequency comb, which carried out all the interesting information of the comb. So what we did, we stabilized the mode spacing of the different mode of the comb by mid-to injection locking. We first feed the QCL with a radio frequency signal, which is approaching the round-trip frequency of the QCL. In this way, the injection locking is active, and you can practically reduce drastically the fluctuation of the frequency spacing between the optical mode. Then what you can do, any mode of the radio frequency comb can be slightly stabilized by means of a reference oscillator and using a phase locking loop. And in this case, there is this stabilization of the spacing between the mode is not present. And so you see an increase linearly of the line width of the bit node. But if you can combine together the two mechanisms, you can simultaneously result in a stabilization of the comb, a full stabilization of the comb, and this is what we did. We were able to reconstruct perfectly our frequency comb emission of the laser, demonstrating that it is really a fully stabilized frequency comb, and we were also able to retrieve the shape of the phase of the individual optical mode of the comb, demonstrating that the spread between the phase of the optical mode is within 50 degrees, and this is compatible with the trend of the GDD, which is predicted by theory. To push the concept forward, of course, one of the most appealing applications of the frequency comb is dual comb spectroscopy, and the importance of using a frequency comb for broadband spectroscopy rely in the exploitation of the frequency accuracy of the comb and also the possibility to spectrally resolve the emission of the frequency comb. To spectrally resolve the emission of the frequency comb, one of the most employed technique is dual comb spectroscopy, and here there is on the side a list of review paper that has been produced in the last year by many groups working in the field of terrestrial QCL to try to employ dual comb spectroscopy for making real experiment in the spectroscopy. Very recently, what we have done, we have combined the advantages of the dual comb spectroscopy that traditionally we also employed in other frequency range with the advantage of having a quantum cascade laser, which is a laser delivering huge amount of optical power to study with high accuracy a molecular profile. And what we have done, again, we have used just the technique that I have showed a few minutes ago, which is multi-heterodyne spectroscopy, in order to retrieve the profile of an absorption from a methanol gas line. And here there is just an animation of what we have done. So there is the amplitude as a function of the rep rate, and there is simultaneously the retrieval of the absorption profile of a methanol molecular transition. And we were able to achieve a precision which is with this gas at the state of the art, 10 to the minus 8 on the central line position of the methanol transition. And with that, I will come to my conclusion. I will not say again anything about the results that I have showed since I lost a few time with this connection, but I would like to give a few perspectives on what I feel is the future of the field of terrestrial quantum cascade laser frequency comb, which of course has a huge amount of potentiality and perspective for metrology, for high precision spectroscopy, for the manipulation of cold molecules and atoms, and also to build up new instruments like, for example, very compact time domain spectrometer that can give a lot of advantages, specifically in terms of optical power in with respect to what it is the state of the art today of the TDS spectroscopy. But I also feel that this kind of devices can provide also many advantages, for example, for near field microscopy, because, for example, scattering near field optical microscopy, which has such a broad optical frequency comb synthesizer, can give a lot of advantages in terms of spectral resolution and bandwidth, for example, to map many local properties of materials, and also to retrieve information about plasmon, phonon polariton, plasmon polariton modes inside bit2D material, and also many other heterostructure from semiconductor and also van der Waals combined in between. And also a very recent perspective that I feel it's very, very important, especially in this era of quantum communication, is that with this frequency comb, we can really think about engineering quantum sensor, quantum imaging devices, and in principle also qubit, made by, for example, exploiting the idea of entangling the teeth of this comb for photonic-based quantum computation and quantum technology. And with that, I would like to close my talk, of course, acknowledging all my group of students and postdocs that they have contributed a lot to the results that I have presented today, and also the list of the collaborators that have worked with us in very strong connection to reach this kind of goal. And I thank you for your attention. I'm so sorry for the problem of the connection. I think that I want a little bit more of the time given to me. Thank you very much.
Thank you, Miriam. Yes, we are a little bit short of time, so we will not have the time to discuss everything. Probably we will have to move on at this point, Miriam. In any case, so questions are here. You are welcome to type your answer if you have time at this point.
Okay, I think that now I only see one question because I disconnected, so probably the other question has been deleted. So I only see one question now.
Okay, so
but I can.
We will have to move on at this point. And
thank you very much.
Thank you very much for participating.
Thank you very much.
It was a mind-blowing set of results. Thanks again for being here today. So at this point, we move on to our contributor talks, and we have today a range of very high quality science, and they are addressing a number of important pressing questions in the field of comms, and in particular in microcoms. So one very important point for a comms technology is to have access to a practical on-chip platform with an efficient low noise comm, and how to do this with laser mode locking technology is what we are going to learn today, thanks to Stijn Cuvier, that is studying towards his PhD degree at the Ghent University. So today in his talk, he will talk about chip-scale electrically pumped 3.5 on silicon nitride frequency comb. Stijn, it's to you. Thank you.
Thank you for the introduction. I'll share my screen. All right, can you see my screen? All right, so optical frequency combs. I guess by now most of you are already familiar with these optical sources that consist of a large number of equally spaced coherent laser lines, because they've gained a lot of interest in recent years. For example, they have proven to be instrumental for scientific frequency metrology and timekeeping. And because of their importance, in 2005, the Nobel Prize in Physics was awarded to Theodore Hensch and John Hall for their work on laser-based precision spectroscopy, including the optical frequency comb technique. Now, as already mentioned in the previous talk, traditionally, such optical frequency combs have been generated using mode-lock lasers, either solid-state titanium sapphire lasers or fiber mode-lock lasers. But of course, to unlock their full potential and to really broaden their range of applications, it is useful to implement such an optical frequency comb generator on a photonic chip. Now, in recent years, there have been a number of different techniques to generate optical frequency combs on a chip. And I just mentioned three popular or well-known methods here on this slide. So Kerr combs, electro-optic combs, and mode-lock lasers on a chip. So the Kerr combs are probably the most famous method to generate a frequency comb on a chip. and they consist of a microring resonator that is optically pumped by an external CW laser. And then through the 4-wave mixing, so through third-order nonlinear interactions in this resonator, you can generate a frequency comb. An alternative way is to use an electro-optic comb. And here one uses a resonator with a phase shifter inside it. And then again, by injecting a CW pump laser, you can generate a frequency comb. Now, the approach that we have been pursuing at Ghent University and IMEC is the mode-lock laser on a chip. So basically, the idea is that we use the original approach that was used originally for generating frequency combs, but translate it to a chip-scale device. So as you can see here on the slide, it consists of a laser cavity, here shown in dark blue, with an amplifier and a central absorber, which is here in the middle of the device. And the central absorber basically enables one to phase lock the different longitudinal modes of the laser so that you get a pulsed laser output corresponding with a frequency comb in the spectral domain. Now, we believe that such mode-lock lasers offer a complementary technology for frequency comb generation, in addition to other comb generation techniques, such as the electro-optic comb and Kerr comb. And the reason is that mode-lock lasers can overcome some of the common drawbacks of alternative technologies. One of the disadvantages is that electro-optic combs and Kerr combs require an optical pump source, and this obviously complicates the integration because it means that you need to butt couple an external laser chip to the chip that contains the resonator. Now, a second disadvantage is that EO combs and Kerr combs typically have repetition rates or comb line spacings on the order of 10 gigahertz or even more. And although this is desirable for a lot of applications, a number of applications require a narrower, smaller comb line spacing, so denser combs. And an example is gas phase spectroscopy, because a lot of gases have absorption features on the order of 1 gigahertz. So this means that you need frequency combs with a line spacing of 1 gigahertz or ideally even less, so that you can accurately sample these spectra. And then the third drawback is that the conversion efficiency of Kerr combs is fundamentally limited to a few percent. So this means that in practice, you will never get a very good power efficiency. And this is also something where mode-lock lasers offer a better perspective. Now, one of the first milestones on mode-lock lasers on a chip was demonstrated in 2017 by Casper van Gasse and his peers, and they demonstrated a 3.5 on silicon mode-lock laser. So you can see here on the figure, it consists of a silicon waveguide cavity and then an indium phosphide-based amplifier and central absorber. And using this topology, they were able to demonstrate a repetition rate of only 1 gigahertz, which is very desirable, as I said, for example, for spectroscopy or dual comb spectroscopy. Here you can also see an animation showing how the laser pulse travels inside this laser cavity and is then coupled out through the grating coupler here and then the optical fiber. Now, to push the performance even further, it is useful to switch to a silicon nitride platform. And the reason is twofold. First of all, silicon nitride does not suffer from two-photon absorption, unlike silicon. So in principle, you can get higher output powers, which are for some applications desirable, for example, for LiDAR. And the second reason is that also the linear losses of silicon nitride are much lower than silicon. So this allows one to enlarge the cavity size so that you can have a narrower comb line spacing, but also increase the photon lifetime because the cavity is larger. So this results in better noise performance. So in the remaining of this talk, I will discuss our recently developed chip-scale electrically pumped 3.5 on silicon nitride mode-lock laser. I will start with the outline of the laser design and the layout. Then I will talk about how we fabricate it, and in particular, the microtransfer printing technique that we use to heterogeneously integrate the 3.5 material on the silicon nitride. And then finally, I will outline some of the key performance results of our laser. So let's start with the laser design. So we start actually with a patterned silicon on insulator wafer with on top two 10 centimeter long silicon nitride spirals, which make up this ring type waveguide cavity. And this silicon nitride, these silicon nitride waveguides have an oxide top cladding, But of course, to enable the integration of 3.5 and a 3.5 amplifier, we need to etch a recess, a trench in this oxide top cladding. So that's what you can see here in the middle of the figure. Now, one of the challenges with the silicon nitride platform is that it is not easy to efficiently couple light from the silicon nitride waveguide to the 3.5 waveguide. And the reason is that silicon nitride and the 3.5 waveguide have a very different refractive index. So the coupling efficiency is rather low if you would directly try to couple from silicon nitride to the 3.5 material. And for that reason, we use a silicon intermediate taper so that the light first can couple from silicon nitride to the silicon, and then from the silicon to the 3.5 waveguide. So that here in the end, we integrate through microtransfer printing this indium phosphide, indium aluminum gallium arsenide based amplifier with the central absorber here in the middle. So to have a closer look at the two-stage taper approach, here you can see again this silicon nitride waveguide and the silicon waveguide and the 3.5 waveguide. So initially the light is in the silicon nitride, then it is coupled to this silicon waveguide underneath. Here we have the recess for the 3.5 integration, and then the light couples from the silicon waveguide to the 3.5 waveguide. And you can see here also a microscope picture showing the same structure, again, the silicon nitride, the silicon, and the 3.5. And then this black line here, this actually indicates the boundary of the recess. And by the way, these markers here, these are actually used for microtransfer printing to have a good alignment of the 3.5 device on the silicon taper. So let's now have a look at the fabrication. So in particular, the microtransfer printing technique. So microtransfer printing is basically a pick and place approach to integrate 3.5 devices on a photonic integrated circuit. So what we do is we use an elastomer stamp, and we can basically pick up a 3.5 device that is pre-processed on its native substrate and then print it using the same stamp on our target photonic circuit. So we start with our target circuit, which is here, in this case, our silicon nitride cavity chip, with at some locations a silicon waveguide to enable efficient coupling. We etch in the oxide top cladding in order to access the waveguides. And then we deposit a thin layer of benzocyclobutane, which basically serves as an adhesive layer for the integration process. Then for the source, for the amplifier, we start from our indium phosphide layer stack, and we pre-process the amplifier on its native indium phosphide substrate. After pre-processing it, we encapsulate the device with a photoresist, which is here shown in brown, so that afterwards we can selectively etch with a wet etch this aluminum indium arsenide layer, so that this 3.5 device is solely supported by this photoresist encapsulation. And then what we can do is we can pick up this 3.5 device with this stamp, and this will cause these tethers, this resist encapsulation, to break at pre-designed locations. And then we can place the 3.5 device in the recess on our cavity. And then finally, we post-process the device in order to define a central absorber and also etch some vias to reach the end contact layer. And then we add final metallization for biasing. So this is what you can see here. This is the final active device. So you can see here the central absorber in the middle. And then on the left and on the right, you have these 600 micron long amplifiers. Then these ellipses here, these are the vias to the end contact layer. And here on the bottom, you see that we have 5 contact pads to conveniently bias the amplifiers and the central absorber. All right, so let's now have a look at the key performance results of our mode lock laser. So here you can see the RF comb of the mode lock laser. So this is obtained by detecting the output of the mode lock laser with a photodetector and then analyzing the resulting signal with an electrical spectrum analyzer. And this result reveals that we have a comb line spacing of 755 megahertz, which is for now the lowest reported repetition rate for a passively mode lock laser. And this is, for example, as I said before, very useful to do high resolution spectroscopy. Now, in addition to the comb density, we also have a quite good noise performance. So to evaluate that, we did a beat note experiment with a tunable Suntech laser, which had a 60 kilohertz optical line width. And then we beat the tunable laser with a mode lock laser output on a photodetector, and again analyze it with an electrical spectrum analyzer. And you can see here this beat note fit, which we fitted with a void fit in blue, which has a line width of 146 kilohertz, which means that the optical line width of the mode lock laser is smaller than this value. And then finally, here you can see the optical spectrum of the laser. So it's centered around 1582 nanometers and spans over approximately 3.27 nanometers within the 10 dB range. So this means that we have over 500 comb lines within this 10 dB bandwidth. All right, so I've discussed the laser design and the silicon nitride cavity. I've talked about how we can integrate the 3.5 amplifier using the microtransfer printing technique. And I've outlined some of the key performance results of our laser, including the comb density and the noise performance. And in addition, our mode lock laser is also offers turnkey operation and does not need an external optical pump source because it is electrically pumped. So that allows one to have a single optical frequency comb chip. I would like to thank my collaborators from Ghent University and IMEC. And if you are interested in our work, I suggest you can follow our research group and myself on Twitter. And if you have any questions, I'll be happy to answer them. But you can also always send me an email. It is here mentioned on the slide. Thank you.
Thank you very much, TJ. This was an excellent talk. Thanks a lot. So I give just 1 second of time to the people to add more questions while I ask you. So you have showed us that, I mean, very impressive results. What can you do to get a broader spectrum of your comb? What are the limitations that you have right now?
Yes, well, we believe that actually by driving the amplifiers a bit stronger, that we can already get a bit of a broader comb. So in the past, quantum well mode lock lasers already demonstrated like comb spans of about several tens of nanometers. But right now our thermal design is actually quite poor. So because there is no silicon waveguide for underneath most of the amplifiers are surrounded by dielectric material and are therefore prone to overheating. So we cannot drive them with a very strong injection current, which also limits the comb width a little bit. For example, if you would compare it with the silicon mode lock laser, which was in terms of thermal performance slightly better, the comb width was a bit broader. But yeah, so thermal design is one aspect, and we also believe that we can multiplex, for example, several amplifiers to cover different wavelength ranges. So that's also an approach to improve this.
That's really amazing. So yeah, thank you. So I will go quickly through the questions. So and I try to merge them in. So we have some questions regarding the losses of your system and especially regarding the back reflection and interconnection between the two materials. So how can you reduce the losses and how important are your connection losses?
Yeah, well, they are quite important because we are already, for the silicon nitride, our losses are 5 dB per meter. So that's already quite low. So at that level, the transition losses of the tapers are indeed becoming important. Ideally, the taper losses are actually very depending on how good the alignment is with the transfer printing. So it's a couple of dBs typically, but we are also we also often use amorphous silicon and as a coupling layer, but here we use silicon, crystalline silicon, which intrinsically has already much lower losses. So this is already some improvement over previously demonstrated 3.5 on silicon nitride devices from our research group. But yeah, you can say it's typically on the order of a few dB coupling losses from the silicon nitride to the 3.5 waveguide.
I see. So attaching to this, so is this somehow limited, you were saying, with your micro printing transfer? So one of our attendees is asking, what is the throughput of this technique?
Well, it can actually be very high because the if I go back to the slide on transfer printing, so we can actually in parallel transfer print many amplifiers at the same time. So we can, these stamps here in this example, there are four amplifiers printed simultaneously, but you can scale this to much more. So in that sense, it's really a wafer scale approach that can enable hundreds of devices being printed in a short time. So yeah.
So a question on the cost. So what do you know, what is the cost for doing one of such devices? Could you give an order of magnitude?
Oh, that's very difficult. Yeah, of course, if it's a prototype device, it will be very costly, but we expect that these devices are useful for a lot of applications. So in that sense, it brings the cost down significantly. So I cannot really give like a number. I have no idea myself. Yeah.
This is, I understand. Just a final question before I thank you again. So one of our attendees is asking if you think that it's possible to do longer cavities in order to reduce the frequency spacing below what you have right now, that is 750 megahertz.
Definitely. I think that's also something we aim to do in the future, but we think we can get close to fiber mode-lock laser performance by using really extremely long silicon nitride cavities and some improvements, some stronger amplifiers and so on. So I think it's possible to get like maybe a few hundred megahertz or even 100 megahertz. We'll see in the future.
Yeah, that's impressive. That is really impressive on chip. So, Stina, I have to close at this point. I will talk to you much for much more time, but this is what we have. So, thank you again for your time with us, and many congratulations for your research and your results.
Thank you.
So, we move now back to quantum cascade lasers, and I'm very happy to introduce David Burghoff today from the University of Notre Dame in the United States. So a central question in quantum cascade lasers, as many of you have also put in the question, is to understand the fundamental mechanism of their locking and their coherence. So David today will talk and focus on a specific type of events, that is the production of a frequency modulated self-sweeping laser. And so today he will explain us why quantum cascade lasers and other semiconductor lasers form frequency modulated cones. Thank you.
Okay,
David.
Thanks. Can you hear me? Okay, great. So today I'm going to be discussing a type of comb you may not be familiar with, which is an FM, or a frequency modulated comb. So if you think about frequency combs, these are they're combs that what that means is that they're evenly spaced in frequency and periodic in time. But that does not necessarily mean that they have to be pulses. So historically, mode-lock lasers are the first type of combs that were developed. We just heard some very nice results on chip-scale mode-lock lasers. And these are based on saturable absorbers, and they produce pulses. But this is for the phases that are linear. If the phases are quadratic, then you actually get this mode of operation, which is basically an FM comb. And it turns out that many semiconductor lasers do this automatically without a saturable absorber. So what an FM comb looks like, it looks like, the intensity that comes out of these things is constant, but the frequency is being periodically swept. And that's actually nice for a lot of applications because you don't have to worry about things like detector saturation. Now, this was somewhat theoretically unexpected and also controversial. So this has been really developed more in the last 3 or 4 years or so. And kind of what I'm going to be discussing is, why this happens. But more generally, I'm going to be telling you about why this new fundamental comb state is actually very analogous to the solitons that you may potentially be familiar with. And these are actually governed by the so-called nonlinear Schrodinger equation, which I won't have too many equations in this, but this one's important. And the reason is that it's basically has a potential that's proportional to the optical phase. And that's what I mean when I say that this is the opposite of a soliton in some sense. So FM combs, like I said, they're very general. They have appeared in many semiconductor lasers, not actually just quantum cascade lasers. And there's actually been hints of this for decades. But this area has kind of been held back by the fact that phase measurements are very hard for FM combs because you can't use nonlinear pulse characterization techniques. You have to use heterodyne measurements. So historically, there's been a lot of emphasis on beat note measurements, but of course that doesn't tell you anything about the phase. Within the last 5 or so years, there's been a lot of groups who have been using the Swiss technique that I developed a few years ago. And what this allows you to do is measure the group delay as a function of frequency, and that is good enough to extract out the temporal profile. And we also heard from Miriam Vitiello about this nice phase technique that was recently developed. So it turns out that the dominant mode of operation for many of these things is linearly chirped FM. So if you look at quantum cascade lasers, interband cascade lasers, quantum well lasers, quantum dot lasers, quantum dash lasers, VXLs, they all produce this FM mode, and it's mostly linearly chirped FM. So if you look at the frequencies over time, these frequency sweeping is basically linear, and the intensity is, well, it's not a pulse. It's also really not quite constant, but we'll call it constant-ish as a general rule. And this has actually been observed over a huge frequency range, so from 2 terahertz up to 300 terahertz. So factor of 150. So it seems like this is a really general phenomenon, and we'd like to be able to explain that. So why is it kind of so mysterious? You might think, okay, well, the physics of lasers are generally pretty well known. What's the issue? If you have a gain medium and inside a cavity, you have some mirrors. Your light propagation is going to be described by Maxwell's equations, and your gain medium is going to be described by the so-called Bloch equations, which describe 2-level systems. This is actually quite complicated. Creatively, these two things combined are called the Maxwell-Bloch equations. But this can get pretty complicated because like for a semiconductor laser, of course, these are both the Bloch equations have to be considered as a function of space and time, and so you have 4 complicated differential equations. So you have the electric field traveling in both directions. And then you also have the population inversion and coherence of the 2-level system. So this is completely correct. Like there's no there's no real physics that's not hiding here. But it's also kind of a nightmare to deal with. If you actually look at it, this is actually for a 3-level system. I don't know, personally, my eyes kind of glaze over when I see this. It's very nonlinear. It's got there's a lot of equations here, and it's hard to get through that. So you can, unsurprisingly, you can do numerical simulations, and you can actually reproduce this linear FM behavior. So there's been a lot of that work, and here's another example. So when you do this, you can produce this linear FM. So what I'm plotting here is on the left is the intensity, on the right is phase, and if you don't know, frequency is basically the derivative of phase. So the intensity inside this Fabry-Perot laser, well, it increases on the inside, but then at the facet, it decreases dramatically. So one of these waves is propagating left, one of them is propagating right. So, all right, that's just due to the regular properties of the laser. If you look at the phase, you see that the phase is in fact parabolic. So if you differentiate this, you'll get linear FM. So, this FM behavior can be predicted. It's just very hard to understand because, you're almost doing numerical experiments at some point. You're changing a parameter and then you're seeing how things change, but you end up affecting a lot of properties of the system. And so we spent some effort on trying to develop an analytical description for understanding the physics and the scaling laws. So there's a lot of, you can read about it in this paper that came out last month. There's a lot of work to do this. I'm not going to talk about that. I'll just give you the very high level overview. You start with the Maxwell-Bloch equations. You solve out the 2-level system. You do make this change a variable to change these two waves that are propagating in two directions, you change it into one wave that is propagating in one direction with periodic boundary conditions. So we call this F. So this is like a normalized field. And then we make this constant amplitude assumption to get to FM combs. And this gives us our nonlinear Schrodinger equation that I mentioned earlier. So this is actually just one equation to describe this system. And this, if you haven't looked at a nonlinear Schrodinger equation before, you might think this is kind of weird. So, on the left-hand side, you have the evolution of the field. On the right-hand side, you have this Hamiltonian. And the Hamiltonian, well, it has this so-called phase potential that I mentioned earlier. So it's if you want to think in terms of wave functions, this is a potential, which is the phase of the wave function, which is really strange to think about. There's some other terms in here which are a little bit more standard. So there's this group velocity dispersion term. So this looks like momentum. You almost always see this in these sorts of nonlinear optical systems. And then you have this source term, which keeps your amplitude constant. So this is basically just due to the fact that you have a laser. And it's really this phase potential term, which is what allows you to have the FM behavior. Oh, and by the way, there's other terms that I'm neglecting. They're not really important right now, like gain bandwidth, for example. So basically what's going to happen is that the group velocity dispersion is going to balance the phase potential to create an FM comb. And the reason this phase potential is generated, it's actually due to an effective cross-steepening nonlinearity at the mirrors. And what this is it's a little bit complicated, but it arises due to the fact that you have a standing wave. And normally you think of a standing wave is going to be, well, what it sounds like, it should be standing. That's true for a single mode laser. But for a multi-mode laser, it's actually kind of time varying. So this is kind of hard to think about, but you can, if you want to, you can think of it as a chi-3 nonlinearity. It's very analogous to like a Raman effect. It's a non-instantaneous chi-3 nonlinearity though. So, all right, this result, it has a really nice parallel to conventional intensity solitons, which also, and it's also similar to mode-locked lasers. And this is, you may have heard of the famous nonlinear Schrodinger equation has an intensity potential. So if you look at this intensity, or if you look at this equation, the potential is proportional to the optical intensity. Here we have this phase potential. So this is kind of the opposite. The regular solitons are, they're famously described by a Seach function, which ends up looking like a pulse, basically, if you don't know what a Seach is. And so the potential has this kind of shape. The intensity is also a pulse, and then you also get a flat frequency. For FM combs, you can solve this, and you get what's basically a Gaussian. So it's a chirped FM, but it has constant intensity up front. So here the potential is a parabola, and the intensity is basically constant, whereas the frequency is fluctuating. So here the waves are, in solitons, the waves are completely localized. FM combs are completely delocalized, the opposites in that sense. And so we're kind of calling these extendons, because soliton is really not an appropriate term for this. But these extendons, you can check them against the numerical theory. Does it actually work? And the answer is yes. So if you turn everything on and wait, you can see that the extendon theory kind of matches with the numerical version. So, here we've plotted the intensity. You can see it's mostly constant, phase, frequency. The only discrepancy is kind of where this phase turns around. That, you call it, it's basically the jump, and it's where the frequency also jumps. And that's because the solution isn't valid there. So if you want to think in the frequency domain, this thing has a relatively flat spectrum, and that's also observed experimentally. You can think of it though as, the laser is just kind of sweeping around periodically, and so that's why the spectrum ends up looking relatively flat. So what we want to learn, what are the scaling laws? I promise that that's what the goal of this was. In terms of physical parameters, you can actually now calculate the actual FM bandwidth. So this is very analogous to, for example, the type of scaling laws that you see with soliton generation in terms of the pulse width. But actually, you know, the FM bandwidth is pretty simple, and it doesn't depend on a lot of things. It depends on the mirror losses of the cavity, depends on the gain, depends on the group velocity dispersion, and it depends on the lifetime, basically. And so that's it. So why semiconductor lasers? Actually, this could be any laser, right? Well, what you need is this large mirror reflectivity, and it has to be at the facet. So anytime that you have something like a unidirectional ring laser, so this is something that we made in our lab, you know, this is not going to work. This is not going to produce an FM cone probably. You know, the gain medium needs to extend to at least one end mirror. So like if you have a solid state laser or a fiber laser, it's not going to work because the gain medium doesn't go to the facet basically. But semiconductor lasers, they have this nice property where the mirror losses are large, and also the gain medium goes right up to them, up to the mirrors basically. And so that's why this is observed typically in semiconductor lasers. So, you know, one last comment, I think of a little bit of time, you know, about group velocity dispersion. You know, this result implies that if you make the group velocity dispersion equal to 0, then you'll get infinite cone bandwidth, which would be amazing. In reality, that does not happen just because we ignored the shape of the gain spectrum. What actually happens if you make the dispersion 0 is it tries to sweep larger than the gain spectrum. And when that happens, basically the intensity falls and the cone totally destabilizes. So if you actually just run the numerical simulations, you can see that this thing is just kind of oscillating in a random way. It's pseudo-random basically. And and in this case, you would not have a cone. This is a multi-mode lasing. So you want your dispersion small because your dispersion being small gives you a large bandwidth, but you don't want it so small that the cone destabilizes. So, you know, in conclusion, we showed that FM combs are a fairly universal phenomenon, basically only described by a few parameters. So you can get them in lots of different kinds of lasers without any, you know, even saturable absorber. But we also said why they mostly appear in semiconductor lasers, and that has to do with the geometry, basically. And the origin is cross-steepening nonlinearity at the mirrors. And the result of this is you get a nonlinear Schrodinger equation with a phase potential. And we call these solutions extendons because they mirror solitons in a lot of different ways. They're kind of like the opposite of a soliton. And so, you know, it turns out that lasers still have things that are buried inside them, and you can still figure out lots of interesting laser dynamics in 2020. So some additional resources, this paper, all this code is available on a GitHub repository. I have a postdoc ad and also Twitter account. So thank you all for your attention.
Thanks, David. That was super, super nice. And so I give a moment to the people to elaborate a couple of questions while I discuss a moment with you. So I was curious, what is the role of the boundary condition of your problem to your extendon?
So the boundary condition is, you know, it ends up being a periodic boundary condition, and it ends up, it's very different from the normal intensity soliton where you're dealing with, you know, usually infinite periodic boundary conditions. We do not currently have an analytical solution that is valid with the boundary condition. That is basically, you know, the solution I showed is invalid at the boundary. Now, practically speaking, that doesn't matter for a certain parameter range. But if you look at this unstable regime that I showed, you can see where it's unstable. It's unstable at the boundary. So this is really kind of the main destabilizing factor of these combs.
Yeah. That's interesting. So we start to have some question. This point very technical. So let's start from the first regarding the numerical methods. So while we are in this step, so can you comment on the type of a numerical method that you use for solving
Yes.
the system?
Yeah. So we did use a split step foray method for this. I think We are not really, I wouldn't say we're like experts in this sort of simulation. We're looking for collaborators in this area. But like that was relatively easy to implement. So
I see. So in the simulation, you use the full system, David. So including the gain and all the parameters that you have neglected in your theory.
Yes, that's right.
Yes. Okay. So this is another thing that is interesting. So you've shown a sort of Ruggiero-Lefebvre-like equation so a Schrödinger-like equation with the source and the loss. I've seen that your losses are quadratic with the field.
So the loss, are you talking about the cold cavity losses?
Yes, I don't know if you.
So the losses actually end up. I kind of skipped over this because this was in that big reverse pyramid that I was showing. But basically, the losses end up buried into the definition of F. So actually, what F does, the difference between F and E is that F already takes into account the losses.
If you go back to here exactly. So I've seen this source term. So before was fine.
Oh.
So I think it was referring to this term that you multiply by IR, right? This square modulus of F.
Oh, sorry. Was there a question?
Yes. So those are the losses. So it's the equation is a little bit different from.
Oh yes. Yeah. I mean that is important. Yes.
Yeah.
I mean that this is basically what makes it different from without this term everything just dies off. This is the term that keeps it lasing basically. So this is that's basically the reason why it ends up being dominated by the phase as opposed to the amplitude, right? So what this is trying to do is it's trying to drive the amplitude to this P naught. And that's why I say this is a phase potential, even though it does have an F squared in it, but this F squared is basically constant. So this is it's not exactly the same. This is a big difference. Let's not undersell that. Yeah.
Okay, so still we are in page 7. So I have a question from an attendee. Can you explain this the standing or better non-standing wave on page 7?
Okay, here we go. Already here.
Yeah.
So so this is what the standing wave looks like if there was no phase basically in the system. So like a regular single mode laser would have this sort of intercavity intensity, and it's standing, so it's not actually doing anything. So this is actually what the standing wave, so basically the total intensity, looks like for an FM comb. So you can actually kind of see that it's still oscillating. And this is ultimately what kind of gives rise to this complicated nonlinearity. So that part kind of gets skipped over just because it's mathematical. And but yeah, it's really due to Actually, let me show this. This nonlinearity, it's very different from from most nonlinearities. So it's third order, but E plus is the field going in one direction, and then E minus is the field propagating the opposite direction. And so that's why we refer to this as cross steepening, because it's actually one field being affected by its counter propagating wave indirectly through this gain grading gain grading is another word for standing wave.
David, thank you very much. So I think that now we have reached our time. It was a very interesting talk. Thanks so much for your time with us today, and congratulations again for your research. So I will move now to our last talk. So Dulcis in Fundo, we are arriving at the last talk of this conference. So frequency formation in microcavity made by quadratic and electro-optic materials is a topic that is acquiring a lot of and increasing popularity. But at this point, there is still a lot of interest and understanding that needs to be obtained. And fundamental understanding in many processes. So today, Nicolas Lambert from the University of Otago, New Zealand, will focus on the role of crystal symmetries in whispering gallery mode microresonators, and will talk to us about electro-optic dual frequency comb and crystal symmetry. Thank you, Nicolas.
Thank you, Alessia. Thanks for that introduction, and thank you for the opportunity to speak at this really nice meeting. So I'm going to discuss some early results from an electro-optic comb realization today. So Maxwell's equations in free space are, of course, linear. So if we want to get different frequencies of radiation to talk to each other, then we need to introduce some material with a non-linearity. And then we have higher order terms in the expression for the polarizability of the material, such as this chi2 term that leads to a dependent on the square of the electric field. And the key thing is that this non-linearity leads to some frequency generation and difference frequency generation. And this allows us to generate new frequencies, which is, of course, what we're really trying to do with a frequency comb. And the idea with an electro-optic frequency comb is that an RF or microwave field creates sidebands on an optical carrier. And if you increase the power of the RF or microwave signal sufficiently, then you get sidebands on those sidebands, and frequencies cascade throughout the spectrum. And with sufficient power, you get an optical frequency comb. And this has been realized several ways in the past. You can do it with a commercial electro-optic modulator. You can use a phase modulator or an intensity modulator. Naively doing it with a single modulator is a little bit problematical because you end up with zeros of amplitude within your spread of comb lines. But by combining the two, you can solve this problem. This has been done. You need quite careful phase control between the drive for the phase modulator and intensity modulator, but this can be done. And you can increase the efficiency of this sort of device by cascading several phase modulators. But these devices are still generally quite inefficient if you get a commercial phase modulator from, say, Thor Labs or whatever. And a really nice way to increase this efficiency is to use resonant enhancement of both the optical field and the microwave field. So first I'll talk about the resonant enhancement for the optical field. And a really natural way to do that is to use a microresonator, which supports whispering gallery modes. So here on the left, we have the typical ray path picture, the naive ray path picture of whispering gallery modes undergoing total internal reflection every time they intersect the boundary between some dielectric and the air. Or in an electric field picture, we see you have a number of nodes and antinodes living around the resonator. And the nice thing about these resonators for frequency combs is that they have a spectrum of modes corresponding to increases in the number of nodes and antinodes around the resonator, and they're all separated by free spectral range. The material we choose to use for this is lithium niobate, which has an excellent transparency around telecoms wavelengths. If you make a lithium niobate whispering gallery mode resonator 5 millimeters in diameter, you'll have a typical free spectral range of about 8 to 9 gigahertz. It does depend a little bit on whether you're looking at the axial or radial polarization of light in the resonator, and that'll be important later. So we make these things by diamond cutting them to shape and then hand polishing them. And if we do that well, we can get Qs of greater than 10 to the 8 for a really, really good one. So that's fine. That's some resonant enhancement for our optical field. But what about our microwave field? So in previous work in our group, we've used a copper microwave cavity. And here we see a photo of it. There's a stadium-shaped inset here with the whispering gallery mode resonator sitting in the middle. And when you put the lid on this thing, this stadium shape with its little pedestal in the middle confines the electric field of the microwaves to live around the edge of the whispering gallery mode resonator. The name of the game here is to maximize the overlap between the microwave field and the optical field. But there's another kind of trick we need to play, and that's we need to get phase matching between the optical field and the microwave field. In any electro-optic device, we need to make sure that these two fields are phase matched so that the electro-optic effect doesn't end up cancelling out over some long propagation distance, or alternatively many orbits of the whispering gallery mode resonator. So in this previous work, we solved the problem by using a higher order mode of the copper cavity. So now, instead of the electric field being uniform across the cavity, first pointing up, then down, it now alternates. So it points up at one side and down at the other, and then swaps over and points down at one side and up at the other. And this maintains the phase matching as the photons run round and round these whispering gallery modes. We can be a bit more precise. This phase matching is, we can be more precise about that by writing down this kind of cartoony integral here. So G here is the coupling between the optical field modes, the input optical field, the output optical field that we're trying to generate, and the microwave field that's driving this coupling. And it's the integral over the mode volume of all these things multiplied by the electro-optic coefficient. That's actually the nonlinearity that's doing this job of letting them talk to each other. So here we have some cartoon going along the x-axis around our whispering gallery mode. And then we can see the input and output optical fields are actually separated by one wavelength. There's one more wavelength in this output optical field than in this input optical field. And if we look in the middle, we can see that they are out of phase there. And then the microwave field, as we go around this resonator, it has one wavelength, essentially. It's positive on one side and negative on the other. And that lets these two orthogonal fields, the input and output field, be coupled together. But we can do this another way, right? We can have a uniform microwave field and a spatially modulated electro-optic coefficient. And this is a little bit like periodic polling, right? We're exploiting the spatial variation of the electro-optic coefficient to do this job. So now on to our device. This is what it looks like. This is a cartoon of it. The whispering gallery mode resonator is now not a disk of lithium niobate, but rather a really thin ring, and it sits on the inner of this loop gap cavity. So it's probably a bit clearer in cross section here on the right. This region here, this hatched region, is the copper microwave cavity. And if we zoom in to this region, we see that there's a thin ring of lithium niobate with a mode volume sitting just there, really near this kind of electrode from the outer of the copper cavity. And the trick is we use an X-cut lithium niobate crystal rather than the Z-cut, which has been used before. And now, as the light runs its way around this whispering gallery mode resonator, it's first traveling along the Z-axis and then along the Y-axis. And it therefore sees different components of the electro-optic tensor depending on where it is around this ring. And we can plot that here. So this is a graph of the chi2 for axially polarized modes and radially polarized modes as you go around this ring. And you can see in both cases, we have this spatial variation. It's positive on one side and negative on the other. And this gives us our phase matching technique. So now onto the experiment. So we drive our our whispering gallery mode resonator on resonance with a particular mode. We can choose the axial or radial polarizations with the polarization controller. And we can also lock to one of these modes with a PDH feedback loop. And then we also drive our microwave resonator at the free spectral range of the whispering gallery mode resonator. So these things have to all be commensurate with each other. And we can look at the output of this with an optical spectrum analyzer. And we find that we do indeed get a frequency comb out, and we have about 40 lines. This structure in the middle is in fact from our laser, which is not quite a single mode as it would have you believe. So here we have on the right a reference with the microwaves turned off. We still see this small substructure. What we care about is this larger structure here. And there's a few things about this comb we might want to characterize. In particular, the stability of the frequency difference between the comb lines. So how stable is this comb over long periods of time? And the way to do that is to take the comb. So we take our generated comb here and we mix it down on a fast photodiode. And then the output of this photodiode gives the beat note between the cones. So we should get the free spectral range back out of this thing. And we care about the line width of this beat note. Now, in fact, the line width is far too narrow to measure directly with, for example, an electronic spectrum analyzer, a microwave spectrum analyzer. So we mix it down again. We have a microwave local oscillator at the drive frequency plus some small offset of around 100 hertz. We mix those together, and this allows us to digitize the signal directly with an oscilloscope. We then take the power spectrum of that, and we can then look at the line width. And we find that this thing's really stable. The line width of that beat note between the cones is about 1 millihertz, and probably less, really. This is pushing our resolution, and this was over 3 hours of acquisition. So there's another thing we can do with this sort of device, and that is generate a dual comb. So the idea with a dual comb is following on from this idea of beating comb lines together. It's a lot easier to do these measurements at microwave frequencies or radio frequencies rather than optical frequencies. So if you have two cones, then you can use one as a reference, one as a probe, beat the comb lines from each comb against the other comb, mix them down to RF frequencies, and this makes your measurement a lot easier. As I've drawn it now, it's not quite the full picture because the offset between combs on the left and on the right is the same. So it's really nice to just offset one comb a little bit to break that symmetry between higher and lower frequencies so that you can uniquely determine which pair of comb lines is generating some particular frequency at RF. So we do that. We again have our carrier tone around 1550. An acoust-optic modulator splits it. So we now have two carriers from the same laser at 100 megahertz. One we align with the axial polarized whispering gallery mode, and the other is going to drive the radially polarized mode. So then we have two microwave sources. Again, one frequency at the free spectral range of the axial modes and one at the free spectral range of the radial mode. So these are two families of modes that are going to give us our two combs. We then come out of our comb, rotate one of these polarizations back onto the other one so that we can beat them together, back into our OSA mixer so that we can look at the RF output. And if you were doing spectroscopy, then your sample would live here and you could look at the effect on that. So this is the RF spectrum from our dual comb. We don't have we can't see very many comb lines yet. We need to improve the efficiency of this device, but it is working to show the beat frequencies between the first few orders. There are some artifacts here that are just from the carrier, from nonlinearities in our measurement chain and the carrier. So we can also care about the stability of the relative stability of these two dual combs. So what's the line width of these peaks? By playing the same trick again, we mix down these megahertz beat notes to a few hundred hertz, digitally sample them, and calculate the power spectrum. And we find that these are really stable as well, around one or two millihertz relative stability. between these two cones. And the reason really for this, there's two reasons. One is that all our frequencies are coming from the same 10 megahertz clock. Everything's phase locked to the same 10 megahertz clock. And the other reason is that the two paths, the light paths for the two cones, they're never separated. They're always accumulating common mode noise from the lithium niobate. And just to summarize, so by using nonlinear whispering gallery mode resonators, microwave cavities, we can generate an electro-optic comb, and we simplify our life a little bit by using crystal symmetries to provide the phase matching. This also allows us to generate dual combs using the two optical polarizations, and we find that the combs that we've generated are really very stable indeed. Finally, I'd just like to acknowledge people here in Otago. We also work with Max Planck Erlangen and Auckland here in New Zealand. I'd like to thank funding from the Royal Society of New Zealand and MBIE. Thank you very much.
Thank you, Nicholas. Thank you a lot. So I will give you another moment to our attendees to place some questions, and while I will ask you. So dual cone spectroscopy, we have seen it also in our previous talk. It's very important. It's a very important technique. So you have a dual comb. How much can you tune your properties, and how can you tailor your device for this kind of application?
Right. So the we can do some fine tuning of the free spectral range by thermally tuning the resonator, and this isn't the ideal geometry for this, but you can also apply static electric fields to tune the two modes. And because they respond differently to electric fields along different crystal axes, then this gives you some freedom to tweak things. But these are only small changes. But by changing the geometry, so by changing the diameter of the whispering gallery mode resonator, you can choose your pulse frequency, so your line spacing. And the other thing you can do is choose a different electro-optic material, which would have different birefringencies. And so that would also change the relative, I mean, it would change the FSRs of the two modes, but it would change them differently because of the different birefringencies. So I think you can, at the time of fabrication, you can make a wide range of choices. Once it's made, you can tweak over a small range, a small parameter range.
I see, and that seems very promising, a very, very promising technique. So I go quickly to the question of our attendees. So first question regards the higher order nonlinearities, because so with the second order effect, do you see also an associated kite-free or maybe a cascaded quadratic effect?
We've never seen that, no. We've not seen that in these combs. Yeah. And maybe we're not, I think probably we're not driving them optically hard enough.
Yeah.
Yeah.
Yeah,
I think that's right. So the power levels, I think the power levels I showed were probably like 1 milliwatt in the carrier, but that's amplified after the comb generation. So the power incident on the resonator is much lower than that, probably a factor of 100 lower than that. So I suspect that the intensities are not high enough.
I see. That's a good point. So another interesting thing regards, so you have shown us different design for your microcavity and your microwave cavity. So how important is the alignment between the two?
It's really key. So the thing that you care about is as I say, the overlap between the microwave field and the optical field. So you can see maybe the thing to look at is this diagram on the right. It's 500 microns from top to bottom of the whispering gallery mode resonator. So a misalignment of 100 microns, say, in the position of this electrode on the outside, and you've got no chance. So we do assemble these things by hand at the moment, and this also limits how small we can make the gap between the electrode and this surface. I think it's 50 microns at the moment. So there's clearly a pathway to improve this device by a more engineered fabrication technique.
I see. That's very, very, very interesting. So I think we have time at least for a final question. So during the dual-com mixing, why one of them has more noise than the other one? Should it be equal for both? That's an interesting question.
In the dual-com mixing, so
yeah.
Right, no. So the black curve I show here is that's from that's all from the two carriers. So that's the noise introduced by the acousto-optic modulator.
I see. I see.
This red curve is the additional noise introduced by the whisper and gallery mode or by our device in general. Presumably due to noise processes within the lithium niobate, which is the usual dominant effect in these cases. What would be a really nice thing to do, which we haven't done yet, is this is just for the first order beat note, is to see how this is affected for higher order beat notes, and to see if this cascading of frequencies adds significant noise at each step, or whether this is all common mode and you kind of lose it.
Yeah. Nicholas, thank you so much. So it was an amazing talk, and I thank you again for being with us today. So you are actually concluding our conference, and at this point, I can just say bye to you all and pass the ball to Andrea, that is going to give the closing remarks. Thank you.
Thank you, Alicia. And thank you, everybody who attended today and also yesterday. I would encourage everyone to, if you missed any of the presentations, they're all going to be posted on our YouTube channel. The ones from yesterday are actively being edited. We unfortunately missed a few of the hot topics at the beginning, so those are going to appear probably this evening or early tomorrow. And this live stream video will also appear in its entirety tomorrow. Most importantly, I would like to thank everybody who supported us, Photonics Media, the Center for Research in Photonics at the University of Ottawa, the Joint Center for Extreme Photonics at the University of Ottawa, and the National Research Council, and the USC Viterbi School of Engineering. They enabled this entire event to be free. So without their help, we probably wouldn't have as many people here as we do. And of course, this wouldn't be possible without my amazing co-chair, Ora Dershef from University of Ottawa. So thank you. Have a great evening. And if you have, 3 or 4 minutes to hang out, it would be great if you could complete our post-event survey, and I will post a link here.